Hey, good morning, everyone. Welcome and thank you for joining us at the first workshop on making sense of data and robotics. We decided to host this workshop because of the increasing importance of robotics data and the scaling up larger models, whether we're training machine learning policies, building large-scale world models, or adapting foundation models for a wide reason. However, it's also apparent that we haven't yet settled on a concrete formula for what data sets should consist of. Should we have data, human video data, simulation data, or something else, and how the criteria for what constitutes good data changes from setting to setting. So this workshop is structured around three core themes. The first being data composition, what data should we include in our data sets? Second being data curation, what data should we keep, drop, or collect next? And finally, data interpretability. How does data shape the behavior of all models that test on? Insights along these axes will enable us to design data sets with better intent as we scale up. Now, the high-level program for the day is as follows. We'll start with 3 invited talks, followed by a coffee break. Before lunch, we'll feature presentations and posters from 35 of our accepted papers. After lunch, we'll reconvene for 3 more talks, a tutorial on data mixing for large language models, and a panel with our speakers. We'll wrap up with rewards and closing remarks. With that, let's get started. The first talk that we have today is by Joseph Lim, who is an associate professor in the School of Artificial Intelligence here at KAIST. Previously, Joseph was an assistant professor at USC, and he completed his PhD at MIT under the guidance of Professor Antonio Torralba, and postdocs under Professor William Freeman and Professor Fei-Fei Li at Stanford University. He has also spent time at Microsoft Research, Adobe Creative Technologies Lab, and Google. With that, please, Joseph, come to the stage, and let's get to our first talk. Disconnected here. Back up.
There we go. Should I unmute my microphone or over Zoom? Just okay, I can just talk. Okay. All right. Nice to see you guys. It's a great honor to give a first talk of this workshop. And in fact, as the title say, maybe it's I'm actually going to argue we may need more than just the data today, and that will be the talk. And I'm probably going to argue what we can do beyond just collecting data. So, as we all know, in AI, NLP, vision, and everything else works really well. And a lot of it is due to data scaling. So we have figured out how to scale the models, and also how to scale the data, and how to collect or use existing data. Now, of course, as a roboticist, we also did the same thing. Engineers, we copy things, right? So what we did is basically collecting large scale data, or also finding ways to collect larger scale data as well. So this was a lot of, past 5 years of effort in robotics. And with this, of course, we have seen great progresses as well. I mean, it's everywhere. It's needless to say, robotics is having a fun time. from industry, from academic labs, and everywhere. Even it's just hobbies these days to show great results in robotics, right? So the question is, in fact, I recently started thinking about doing startup. So that's actually how all these talks kind of got motivated. So can we actually use this for real world problems? And of course, I'm exaggerating a lot of things, but at the end of the day, let's take a few examples here. And this is like, if we want to solve like long horizon problem, it has a lot of issues. It's not my video, but it's we have seen this a lot. It's not just that. If we want to solve anything that requires precision, it's also the same thing. It does a lot of cool things. It works sort of, but at the end of the day, it doesn't get the job done, right? It has a lot of problem, and I guess I will associate it to something similar to hallucination. It sort of looks correct. If you zoom out, it looks like it's doing right behavior, but it doesn't get the job done. And then, of course, if you look at this, how many of you actually want to use this in your real world home applications or manufacturing, whatever? It's a super slow, and it's not. It just doesn't make up or make. And even worse, human alignment issue. And I'm sure you have seen this type of video here and there in the media, right? It gets crazy sometimes. So how can we solve this problem? Of course, the easiest and maybe the best way right now, we can just collect a lot of data, right? We just collect more and more, and that will work maybe in a way. And I guess Ken next, I think we'll talk about this. I've already just slide, I copied it. We can basically get the data, but even in NLP, compared to that, we basically need, according to Ken, 100,000 years, 10,000 years. And that said, also, even NLP, with that amount of data, it still doesn't work well. So what can we do beyond just collecting data? So of course, again, it's a simple idea. So data scaling is a great idea, and we can collect a lot of data as a roboticist. But at the end of the day, maybe we can do augmentation. We can maybe squeeze out more from just existing data. What can we do? So of course, one of the things people do is data augmentation, especially from Sim to Real or working with synthetic data, especially with the Gen AI. We can generate as many data as we want. And also sometimes people do trajectory stitching. So we have been pretty clever about data augmentation, and that's one way to go. But the other part I want to emphasize today is about this policy augmentation. So we already figured out how to do a lot of small problems, especially using with classic robotics solutions or just learning-based approaches. But whatever, we have several ways to solve problems. So the question is, how do we empower them together? How do we stitch them together so that we can use the existing method and existing data so that we can solve bigger problems? So that will be the theme. And just as sort of a heads up, so both papers I'm presenting today are basically submitted 2 days ago. So I'm also still learning about the papers too. So we'll talk about that. So one topic is going to be about long horizon. So while I said it's long horizon, it's basically about composition problems of robotics. So how can we actually compose different policies or different skills so we can solve the longer horizon task? And then the other problem is also something I showed in the video. A lot of learned policies are super slow. It's like usually a lot of videos receive the 5x, 10x, and whatever. So how can we make it a little faster at least? So that's basically one other domain we're talking about. So both are in submission to iClear right now. So the first topic, like we talk about long horizon. So long horizon task appears everywhere. And also we have seen again a lot of tabletop manipulation tasks that work pretty well. I'm pretty sure you will see tons of videos over this conference that shows column folding or assembly, and a lot of this. So we have pretty good policies or fair policies for tabletop manipulations. But what about mobility? So how do we actually add mobility to this, right? So one way, again, as a data-driven approach, I guess one way we can do this, we just collect a lot of data. We just collect a long horizon task that actually does move robots around and then pick up the objects, and we can just get more and more data like this. But of course, the problem is, as the data gets longer, as the mobility gets longer, data-driven approach will become exponentially harder, and it will not scale well. And even worse, a lot of policies we train, even the state-of-art sort of method, basically has, yeah, it's very sensitive to the initial pose as well. So depending on where you exactly start, sometimes it works really well, and even just a few degrees tilted, it just miserably fails too. Right, so it's a lot of policies we haven't seen that will behaving this way. Same thing here as well. So if we have some good initial state, then it can open this door pretty well. Right, so pretty good. But just by tilting it a little bit, again, this is a state-of-art method. It just fails. So what can we do about that is the question. Again, we can just collect lots of data, get more data, train again, and we keep on trying until forever. But instead of that, what we are proposing is basically doing this. So instead of basically doing everything in a learned manipulation policy, what we can do is we can basically do things in three sequences, right? The first one is we first decide what is a good initial pose. And then the second, we'll go to the good initial pose. And third, then start the policy. So if we can actually break it down the problem into these three steps, I guess it will work pretty well because we have at least some reasonable policy. And we know we went to the good initial pose or state for that policy. So it should at least work somehow. So basically this part, especially the number two, the mobility part, we have figured out pretty well, especially using classic method also and reinforced learning and whatever. And the third part is something we have in the whole community has been pouring a lot of effort for having good tabletop manipulation policies. So really what we need to focus on in this paper is how do we decide, how do we detect the initial pose, right? And what we claim is this can be trained with small amount of data. Okay. There's a poster in another workshop here that will discuss in the details. So I'm not going to go with every single details, but our method basically again is just basically what we call is an end-to-end network, navigation to manipulation network. What it does is just takes all this 3D point cloud as an input, and it outputs the distribution of the good initial pose of the policy we want to execute, and that collecting that, how to collect that and how to train that network is the main key point. And what we wanted in this network, the power of it, the main features were we wanted this policy, this network to be dynamic and also cover the multimodality of the initial pose. And lastly, it can cover varying pose, varying viewpoints. So that's why we were working with the 3D point cloud. So again, I'll skip this part of the details. But what we can just show is it actually can find good initial pose for, again, this one in simulation first, that it can find good initial pose to execute the policy. So it can literally just compose the mobility part and then the policy we have. So any given policy, what we basically end up doing is we basically find good execution initial pose. Okay. And of course, there's a plot and everything. That's just like every paper we have good numbers. So, but what I think is more cool is to show this video. So what we end up doing is we can consecutively pick up this ramp by finding a good execution initial point of this specific policy again. Yeah, I guess you get the idea. So then now this is about pushing this chair. So you can see on the top right corner, it keeps predicting as the chair is moving, it keeps predicting where the robot should go. to push this chair up in a dynamic sense. So once again. Okay. So you can see this is a very fast inference, but also it's not just pushing chair. If you want to use laptop, it's also saying there's a demonstrator move around our predictor, basically end-to-end network can predict where the robot should go to execute using laptop policy here. Also other tasks as well. And needless to say, we can also scale to unseen environments or unseen humans or unseen objects as well. So that's basically it can work in unseen environments as well. Okay. So, yeah. So again, this was about basically bridging basically both the existing navigation policy or method with our existing or pre-trained manipulation policy, so that it can we don't have to collect the new data for longer horizon, especially specifically for mobile manipulation tests here. By breaking it down to mobile part and also manipulation. Okay. All right. So the next is about the speed. So we also already know by watching a lot of videos online, a lot of manipulations are pretty slow. And why is that? So let's take a look at this first. So compared to humans on the right side, robots are extremely slower, right? And imagine, you're building a startup for picking up objects. I don't think anyone will use the robot on the left side, for example. I mean, apart from how reliable it is, especially if we want to do, real world problems. And so execution speed is very critical for real world problems, and time is money, right? So why is that happening, and how can we solve this issue? So one of the reasons robot is slow is because our calibration data or our demonstration data is often slow too, because it's very hard to control. I don't know how many of you actually tried it, but when you actually try to use it to do any sophisticated test, it's very hard, no matter how good devices are yet. So that's basically why it's slow. So what can we do? Obviously, we just somehow we can collect faster data. While collecting faster data, the policy gets faster. It actually works too. It's one way to make it happen, but it's not easy to do that. So collecting fast data is hard and also expensive. So what is the second approach we can take is by increasing action frequency. So we already have collected data. We can just make it faster. We play fast forward. So it works in some sense, but also then it will have a lot of overshooting issue. So which means it actually just move too fast, it crosses over the target and miss the target and whatever. So it actually doesn't always scale too well, especially for high precision requirement task. So that's an issue. So so this is kind of like what happens. So all we did is just we fast forwarded data. So basically increasing action frequency and train a network. Same exact environment, but it actually doesn't work anymore. So one other approach we can actually take from here on is if we know the dynamics of robots, what we can do is we can basically speed up by maintaining by basically doing optimization, time-step optimization, which is by a paper from CoRL 2018. So what it does is once we have trajectory, we try to find an optimal time point to stop and velocity to get to the target points of the trajectory while making the trajectory as close as possible. So it's basically it's simple optimization essentially, but then there is a problem also because it's action chunking. So when you do action chunking from one to the other trajectory, then there's a discontinuity and optimization becomes much harder. So what we ended up doing is basically find a way. I'm not going to go into details of this one again, but with the inference delay, what we end up doing is we basically do roll out multiple trajectories and find the one that actually has minimal curvature, so we can make a smooth transition and then do optimization. So that's basically a simple trick we applied it. And there's a little bit of proof why this is good and whatnot. But at the end of the day, with this method, we can basically make so much faster. And on the left is basically state-of-art method, pi 0.5. And we just apply our optimization tricks on top of it. You can see the speed difference is pretty big. So in this case, we did 2x. And also another video here as well. In this case, we applied it to the diffusion policy. Same test, the same data and everything. Even for relatively high precision requirement data test, you can actually achieve it much faster. In this case, it was 4 times faster, roughly speaking. And yeah, and of course, there's a number and whatnot. Again, to consistently faster, it makes it everything smooth. We are going to archive the paper fairly soon after my students wake up, and then they can work back on the after deadline. So we will do that, and then you can check out our paper online later. Okay. So again, the main idea of this one again is the same. So we have original policy. You don't have to get any more data. All we did is we applied this classic planar optimization on top of it to speed up the policy by 2, 3, 4 times faster. Okay. So that's basically the main theme of this talk today. So our goal and our several line of work in our lab these days is about how do we actually use existing data or policy to make things more faster, or can cover the long horizon tests, or even other tests like high precision or safety related issues too. So with that, I will conclude my talk. Do I take a question too? Yeah.
Similar issues.
You didn't mind for one quick question before we move on to our next talk. Yeah, sorry, you have to see. Sorry, you have to see loudly.
Yeah. I guess it's taking
Oh, it's just your screen.
Right. That's a good question.
Oh, right. That's a good question. We haven't done that part. But actually, while we were brainstorming, we were thinking of how do we actually deal with the dynamics of the objects or environments. I guess we'll probably deal with, I guess we can use one model and apply it, but it's a good. Thanks.
How's that? Yeah.
Right.
Yourself. Okay. Great. Yeah.
Our next speaker is Professor Ken Goldberg. Professor Ken Goldberg is the president of the Robot Learning Foundation and chair of Berkeley AI Research Lab Steering Committee. He is a co-founder of Ambi Robotics and Jacobi Robotics, and is the William S. Foy Distinguished Chair of Engineering at UC Berkeley, where he leads research in robotics and automation, including grasping, manipulation, and learning for applications in industry, homes, agriculture, and robot-assisted surgery. Ken?
Thank you. Okay, thank you very much, and I appreciate Joseph's talk, and it's really set up perfectly what I want to say. I'm going to cover this really quickly, and I think we're all in agreement here. We're all asking the same question: when is this ChatGPT moment for robotics? And there's a mantra that we hear a lot in California, especially of data solve vision, data solve language. Therefore, data is going to solve robotics. And I want to say, first of all, I agree. I actually think it's going to happen. But the question is when. Okay, so data is all you need. I mean, we look at Waymo as a case study, and they're very successful. But we can compare it with Tesla. And Tesla is out there driving, collecting data from all the vehicles. In fact, there's an estimate today of like 9 billion miles of training data compared to 20 million for Waymo, which is a factor of about 500. So Tesla has a lot more data. Therefore, Tesla should be doing much better. But actually, no, they're not. They're actually, I mean, you can quibble about these numbers, but Tesla's actually out there operating with fully autonomous taxis, very low accident rate, and Tesla seems to be way behind. So data is not the only thing that's necessary. Now, I know there's a lot of other factors. But I think one thing that's important to keep in mind is that when you look at these cars, and I've talked to Vincent and others at Waymo, and there's something else going on here, which I refer to as good old-fashioned engineering. And that is lots of other components that are working together with large models. And those particularly with the characteristic of good old-fashioned engineering is modularity, that you have modules that you can compose together. And there's a lot of benefits to that in terms of testing and evaluation and being able to replace elements. Of course, there's a lot of benefits to algorithms and interpretability, and then there's lots of metrics that we've developed over the last 400 years. So this is also true in really even large LLMs like ChatGPT. If you look under the hood, there's actually quite a bit of good old-fashioned engineering going on there. There's a lot of components and databases and systems engineering that goes on, that it's not really end-to-end or monolithic systems. So this pure end-to-end, and I know that many of you have this idea, you want to be purist, you don't want to cheat with engineering. And so I want to push back on that. I just don't like this idea of characterizing that as cheating. Now, OpenX embodiment, there's a lot of tasks, a lot of data that's in that data set. And if you look at them really closely, almost all of these are pick and place tasks. You're essentially picking object 0 and placing it in object 1. Now, it turns out we actually know how to do that with good old-fashioned engineering. In fact, that's chapter 3 of Russ Tedra's textbook, is pick object 0 and place it in object 1. Okay, so that's very, very well understood. And it's basically good old-fashioned engineering. You have modularity. You have a vision module that detects the object. You have a grasping module that decides where to grasp it, and then you have motion planning that gets you the object and drops it in the bowl. So there's also lots of cool engineering metrics that have gone on under the hood that have been developed over the years that are very sophisticated for dealing with good old-fashioned engineering. Now, I know what some of you are thinking. As one of my students said when we were cleaning up the lab, she said, well, let's get rid of this. Well, I was like, I don't really want to get rid of it yet. And, I still think there's some value in it. Now, this is how I think about it. Large models, I love them. I know that's why we're all here, but sometimes good old-fashioned engineering gets the job done. Okay, so I want to just briefly say, give you a quick detour into our work in grasping. So it was motivated by ImageNet, and Dex-Net was essentially the analogous idea. This is back in 2016 to develop a very large data set for training. And in our case, it was not images with labels, but it was three-dimensional objects with grasps. And this is really the work of Jeff Mahler and a number of others, and it produced very, very good results. I won't go into, I don't have time to go into details of how that works, but it was a matter of building our own data set in SIM, but using a lot of very structured domain randomization, and then being able to train a model. And so we built a company on this. We've been working for 7 years now to taking this to market. We are focusing on a particular area, which is logistics, basically package sorting. And here's our system. It's called AmbiSort, and it picks objects out of bins, packages out of bins, scans them for the zip code, and then place them into smaller bins depending on the zip code. And this has to run really fast to get, according to Joseph's point, that you cannot, every second counts, right? They want throughput, picks per hour. They really want to go up. And when we published on Dex-Net, we were about 200 to 300. Now we're over 500 with these systems. We've had them sorting. They're actually sorting as we speak all across the United States. And I'm happy to say that at this point, we've sorted over 100 million packages in real environments. Now you might say, well, isn't that a demonstration that data is all you need? Because you use data, right? That was the key. But no, actually under the hood, there's a lot of good old-fashioned engineering. And I can testify to that because I watched the guys build these systems, and there's lots of modules that go into it. In fact, one big key piece is the motion plan. And the motion planning is actually good old-fashioned engineering mixed with a little bit of deep learning, because we seed the optimal motions with a pre-trained data set. And this is a whole other side step, but it's basically the idea is that you're combining good old-fashioned engineering with some deep learning for speed. So scaling robot data, I want to come back to this. And first of all, again, I want to reemphasize, I know the bitter lesson. I accept the bitter lesson. I'm not denying that this is going to work. You know, I think, some people might say, well, Goldberg has his head in the sand. No, I'm not. I'm not denying, okay? I'm not a denier. But I'm just saying, when is it gonna happen? All right, so I wanna I will happen, but I wanna put some context in it. So this ChatGPT moment, as Joseph showed this video, or the end result of this video, this is a way of thinking about the data, let's see, that we have for robots is incredibly small compared to the data that's available for LLMs and VLMs. I mean, you can make this comparison. Michael Black had this idea of comparing the amount of data in an LLM based on how long would it take a human to read all the text that was used for training. And that answer comes out to 100,000 years. And if you look at elapsed time for a robot being trained by hand, let's say for teleop, we have Pi Zero came out last year with 1 year of data, and that's a big gap. So in fact, it's even more complicated because the state space is very, very high for robotics. We might be controlling multiple joints, at least 6. So it's not clear that even with the same amount of data, we have enough. Now, how are we going to close it? So one idea is simulation. Joseph just talked about this. It works really well for UAVs, and you can simulate them and then run them in real, and that works beautifully. And also seems to work surprisingly well for locomotion and for whole body acrobatics. So we see these results almost every day. There's a new one. They're amazing and really impressive. And this is largely trained on RL and in simulation. But manipulation itself, actually picking objects up, turns out to be extremely difficult to simulate. And we can talk about, I hope we'll have a chance to talk about that during CoRL this week. The other idea is YouTube videos, lots of data out there. And the idea is, can we extract three-dimensional structure and forces, dynamics from that? Now, NVIDIA has been mining a lot of YouTube videos, but it's interesting. It's very good at world models predicting next video frames, but not so good at actually generating real robot data. So, of course, it's human teleop, and people are actually out there working, again, as we speak, collecting data. And it's been relatively interesting. There's some very promising successes. And but I want to propose another thing that I think has been understudied, at least in academia, is data flywheels. And what that is, what I want to go back to the story of Ambi, while we've been collecting all this data, while we've been sorting these packages, we've been collecting data. So we have a dashboard where we collect data from all the different sites. And it's largely motivated initially by maintenance, because we wanted to keep an eye on all these systems. But we also collected and saved all that data. And actually, when we added it up, after 4 years, we had accumulated 200,000 hours of data from real robots and real environments and with real packages. So that's about 22 years worth of elapsed time of data that we've collected. And we've actually started mining that, in other words, using it to build a large model. And it turns out that for a generative model based on that, it actually just 1% of it, because that's all we can afford right now to process, has been able to outperform our existing, our earlier grasp prediction model. So we've also been using, so the idea of the flywheel is you come up with some new idea, some new technology, and innovate, and then you commercialize that, which is a big step, by the way, that's where the good old-fashioned engineering often comes in. And then once you get to that point, you can start collecting data, and then you get better, systems get better, and you can also start doing adjacent tasks. So we've also been looking at the adjacent task of placing objects, and that is a new product that we just announced at Ambi called AmbiStack, and that stacks packages. It's a dual of picking. And the idea is you want to do this as efficiently as possible. It's basically the Tetris problem, but in 3D. Now, it's notoriously NP hard even in 2D. So we got something like this, about 35% densities. But after training with RL, we're actually, and this is where SIM actually works well, we're able to bring this up to approximately 90% density. So here's our system, and we've been selling these, working with shipping companies on how to do this better and better. So this is the idea of the data flywheel, is to get a system running, whatever it takes, then collect data on it. Okay, now coming back, this is exactly what Waymo's doing, right? They have a system, they've got it working, now they collect more data, and the system just gets better and better. And I want to say, Gemini Robotics just announced a new version, 1.5. a couple days ago, again, that's also a case where they're getting this data, putting it out there, and they're also using, by the way, the data from VLMs very effectively. We know that under the hood, the ER up there is about VLMs and combining those in intelligent ways with VLAs. Dyna Robotics is here. They're setting up a great demo. I can't wait to see it. They are doing this too. I would say that I would consider this a flywheel in the sense that they really fine-tuned it on one task, one folding, but only one type of object, or one folding towels, but they do it really, really well. And as they do it, it starts succeeding and they get better and better and better. This is also somewhat of the case what's going on with Boston Dynamics and their collaboration with Toyota Research. Also want to point out, if you read their blog report carefully, there's several mentions of algorithms in there. So they're doing also this idea of large models, but with bits of good old-fashioned engineering underneath. I also think I see this in a new paper that Sharon put out very recently, where she was talking about using some form of control barrier functions. But basically what she's doing is there's a meta model that's watching another end-to-end model, and when it goes out of distribution, it basically switches to a new model that pushes it back into distribution. So I consider that a kind of form of good old-fashioned engineering. It's multiple models, but using them in a structured way with modules and being able to switch between them. Okay, so just coming back, the robot data gap. And do I have a little more time? Yes. Okay, so I want to say that I want to tell you about a couple of the new things. Robot data management is, and I hope we'll talk about all these today, but the OXE data set is wonderful. But if you actually look at it, we break it down, it's actually only a small amount of it is really usable for manipulation. There's a lot of other stuff in there, and it's kind of, well, it's a little crufty. And so we've been thinking about how do we go in and clean it and manage it a little bit. One idea is this idea of RoboDM, which is a data management approach. And this was a paper that we reported at ICRA this year. And the idea is, how do we extract, if you want to do a particular task, how do you extract relevant trajectories, relevant data from that large data set? And it's not only just finding the trajectories, but you have to find the right keyframes within those trajectories. And that really is very, very tricky, and it can be done manually. It's very, very time consuming. So RoboDM is essentially a containerized approach, sort of like Docker, but basically you're setting up these containers where each trajectory, each demonstration is going in and being time aligned and indexed in such a way that you can find the relevant segments that you want. And we've been able to show that we can also compress the data effectively using some pretty standard big compression techniques, but we can get dramatic compressions over what was done initially. So this is a paper from ICRA, you can look it up, but that we're able, with a lossy and a lossless approach, that this is more effective than a number of the methods that are being used out there. I also want to tell you about Robo2VLM. We've been using VLMs to clean data. And I know a number of people are thinking along similar lines. This paper was just accepted for NeurIPS. And the idea Eric Chen and Shuangyu Shi have come up with is basically mining the each individual trajectory and asking VLMs to confirm if it's calibrated properly, if the lighting is okay, if the objects are occluded, and even if the task was completed successfully, which is very interesting because oftentimes it was labeled, but maybe improperly. There's all kinds of queries that you can extract from these robot data, and it's a really very rich source. So they were able to generate 60,000 VQA queries from a very small subset of the OXE data set. Okay, and then there's another thing I do, which is augmentation, also that Joseph mentioned, where you can augment data and maybe transform it into translate it for other embodiments. So this is something else we've been looking at. A lot of the data in OXE is for the Franco robot. It's a very uneven distribution. So it looks like this, right, for this subset. And so what we were able to do is move this to by in-painting, very carefully take the Franca examples and the different Franca grippers and compose it for different arms, different grippers. So here we're able to amplify the data set as it originally formed and build it back up to a very large, clean data set for different embodiments. Okay, the very last thing I'll mention is a paper that's going to be presented tomorrow. Good, perfect time. And this is Justin Yu and Max Fu, who have been asking, how can we scale simulation? And one of the things they're asking is specifically around quasi-static manipulation. That is manipulation that is just basically position-based. And that turns out to be a fairly large subset of overall manipulation. That's just what you're trying to pick in place, right? Coming back to that, or just push something or do something like that. So we typically in simulation, we have a lot of baggage, a lot of complexity in terms of all the physics and dynamics, forces that have to go into it, right? So what if we strip all that out? So we just take the simulation, we just focus on the visual, the rendering. That turns out to be very easy to do. You know, it's lab, you can just turn off all the physics and just have the rendering. So there's no dynamics anymore. And our hypothesis is that that might be just the right subset of simulation that matches the subset of manipulation. Sorry, the subset of simulation matches the right subset of manipulation. So that's the idea behind what we're calling real to sim to real to render to real. And again, as rendering is a subset of sim. Okay, thank you.
One, maybe two questions. Yes. Yes.
Yeah. Hi.
So very thanks. In one debate that you brought up is between end-to-end versus robotic. And my understanding of the vision, all the answers are both.
Yes.
Just as well, the issues we have quite. I mean, patients, you only learn your panel and moving up versus, for example, reinforcement, but then be a mixture of both. I think a lot of people on the end-to-end side only make the assumption that the patient values versus.
Okay, great. No, but actually, that's a great point. That's another argument, and I hope we have that later today, but I think you're right about it. Basically saying, is it just all imitation learning, or is it, stops here. Is it reinforcement learning? Absolutely, reinforcement learning has a very important role, right? And I think that, again, where simulation can get better, that can do that. Need reset and iteration to get reinforcement learning and get to that. So I think that's, and again, I'm not saying that simulation will never have simulation for manipulation. I'm just saying there's a gap like that. There's such a real gap in manipulation. It's still very wide. Don't be such a pure. Don't be such a pure. Forget it when you're young. Feel it. But I guess over time.
What then? Thank you so much. Now your next talk will be from Dr. Marco Pavone, who's an associate professor of aeronautics and astronautics at Stanford University, where he directs the Autonomous Systems Laboratory. He also leads AV research at NVIDIA. Before joining Stanford, he was a research technologist within the robotics section at the NASA Jet Propulsion Laboratory, and received a PhD degree in aeronautics and astronautics from MIT in 2010. So thank you so much for Marco, and looking forward to this exciting talk.
All right. Thank you very much for the invitation. I think my presentation is a very nice continuation of Ken's presentation, since it is about building a data flywheel specifically for building reasoning models in physical AI. In particular, we'll share our work in the context of building reasoning models for autonomous driving, with the idea that many of the ideas apply equally well to the field of robotics. Now, the premise of this talk is that foundation models provide several opportunities to accelerate the development of physical AI systems in general and AV system, autonomous vehicle systems in particular. So here, just to be precise, by a foundational model, I mean a model that has been pre-trained on raw data, typically at internet scale and in a self-supervised fashion, and it can be then adapted to a wide range of downstream tasks. Typical example of foundation models include vision language models, video generation models, and so on and so forth. Now, they're not quite yet at the level of one giant model that can ingest any data modality that can be adapted to any possible downstream use case. But this idea of pre-training on very broad data and then adapting to downstream tasks has proven useful to a variety of different applications. Now, NVIDIA indeed has been building foundation models specifically for the purposes of physical AI, such as autonomous vehicle and robotics. In particular, the foundation model for physical AI at NVIDIA goes under the name of Cosmos, which is indeed a family of multiple foundation models, including Cosmos Predict and Cosmos Transfer that allow you to generate videos out of text prompts, for example, or more structured inputs. This is very useful, for example, for synthetic data generation or even for simulation. Cosmos Embed, which is essentially a video text embedder that allows you to build latent representations that can then be used later on for different downstream use cases, such as data curation and data search, and Cosmos Reason, which is a vision language action model for multimodal reasoning. Now, then the question is, with all this generalist knowledge that is acquired through internet scale pre-training, how can we use this generalist knowledge for the purposes of building autonomy stacks? And the answer is in multiple ways. Foundation models can help us both with accelerating AV development processes, such as data generation, data curation, sensor traffic simulation, safety validation, as well as, of course, the onboard stack by providing more capable end-to-end architectures, or, for example, by providing an avenue to build explainability and introspection into the system. We can think of having a large model in the cloud that helps with building the autonomy stack, and a smaller, yet very capable model running on the vehicle. As also pointed out by Ken, of course, we shouldn't view AV development or robotics development as a static sequential process. It is part of a data flywheel, whereby models are used to train the model that goes into the robot. Then the robot acquires new data that is then used to retrain the models in the cloud. And every time that you go through this cycle becomes more effective because all the models become better. So this is really a self-accelerating flywheel. It's not just a data cycle. Now, what I'm going to do in this talk is to talk a bit more about our work on accelerating the data flywheel for autonomous vehicle systems, particularly through the lens of generating reasoning data to train reasoning vision language action models for autonomous driving. Let me give you a little bit of context first. So for the past couple of years, we've been working on building end-to-end differentiable models for autonomous driving by essentially leveraging a number of lessons learned from the development of foundation models. For example, the use of self-supervised losses, such as video generation and next token generation, the use of large autoregressive backbones that could be trained from scratch or be pre-trained, for example, on language generation tasks, and then the use of powerful vision encoders for the camera inputs. Now, we have now fielded these end-to-end models in the NVIDIA AV program, and here you can see some examples of the behaviors that we have observed. So these models are now part of the production pipeline. NVIDIA is working on in the field of L2++, L3 for now. And you can see that with these models, we can actually accomplish very challenging maneuvers with a human-like feel, something that is quite difficult to achieve with a more classical stack. Now, back to Ken's point, doesn't mean that we are getting rid of models. Of course, we view the end-to-end model as part of a broader policy where, for example, you have a parallel stack based on a more classical architecture, model-based architecture that provides safety guardrails, consistency checks, and so on and so forth, which is still necessary if you want to achieve the level of availability that is needed, at least for autonomous driving applications. End-to-end architectures per se are not there yet and won't be there for a while. But a combination of the two is actually very, very impactful. And this is really production level experiments. Now, motivated by these advances, then we have gone one step further. So basically moving from a backbone that was pre-trained from scratch to a backbone that was pre-trained on the task of language generation. And immediately we see that the task of language pre-training actually synergizes quite well with the task of driving. What I'm showing here on the plot on the right, on the x-axis, you see the number of epochs used to train the model. On the y-axis, we measure the quality of driving according to one metric, ADE. It's not too important here. The lower, the better. So you can see that starting with a language pre-trained backbone, we converge faster and to a better steady state, which corroborates some earlier findings from a paper that we published last year, that indeed language pre-training, perhaps because of its inherent structure, synergizes well with the task of driving. And here we're also showing some examples of driving with a vision language action model in a neural reconstructed environment. And we can reason, for example, about the construction zone and other difficult cases with a fraction of the data that would be needed without language pre-training. But there's much more on the horizon. So we are currently witnessing this year a shift from training time intelligence to test time intelligence. That essentially means that the stack is endowed with an element of real-time planning. All of us are by now familiar with the large reasoning models such as DeepSeek that have shown amazing capabilities in the context of, for example, solving complicated tasks, for example, math problems. But autonomous driving is eminently a reasoning task. Well, I have a decision-making background, so I like to think as autonomous driving as eminently a reasoning task. So it stands to reason that the reasoning model could provide an additional boost to the capabilities of an end-to-end autonomy stack. Now, just to be clear here, by reasoning, I don't mean human cognition. Here by reasoning, I mean a scaffolded statistical process that produces traces resembling human-like reasoning. But pragmatically, that's what we care about. By reasoning trace, let me just give you an example to be a bit more concrete. So for example, here we have a video of a human that is chasing a cat, a reasoning trace that actually is generated by our reasoning trace generation pipeline that I will show you in a second. You see that basically reasoning trace entails breaking down the problem into key steps, what's happening. So there are two cars that are stopped, why there is a risk. Well, there is a person that is chasing a cat, and what should they do next? If the model can break down the problem step by step, that definitely has the potential to improve trajectory generation by making it more contextually aware. Now, the question though is how do we elicit reasoning from a vision language action model? This actually entails a number of different steps, starting from pre-training. So we want to start with our vision language action model and make it more 3D ground space, 3D space task grounded, and also a little bit more aware of embodied applications. Then we go into eliciting reasoning stage, and there are a number of techniques at our disposal, like for example, using a chain of thought reasoning traces, perhaps human labeled or auto-labeled for as a supervisory signal, or leveraging reinforcement learning with verifiable rewards. And then there is an additional step, which is very important, particularly for autonomous driving, which is the alignment step. We want to make sure that the reasoning trace reflects the action that the model outputs for a number of reasons, in order to gain as much as possible from the reasoning process. But at the same time, for example, if we want to use the reasoning trace as a monitor for safety checks, we want to make sure that, of course, the reasoning trace reflects what we are doing. I like to think that a typical case of a misalignment is when I play tennis. I like playing tennis, but I'm not a great tennis player. Oftentimes, I do have my strategy very clear, but for whatever reason, my body does something else. We don't want that. We want alignment. Okay, so now that I made fun of myself, let me talk a little bit more about how do we build reasoning data at scale so that we can elicit reasoning out of these models. Indeed, generating reasoning traces is hard, actually somewhat harder than I thought at the beginning, for a number of reasons. There are many challenges. One of them is that the scope is a bit ambiguous with respect to more standard vision tasks. There might be annotation drifts, something that people feel are important, other people may feel they're not important, and somehow you have to devise some guidelines that you can then encode in your auto-labeling pipeline. and avoid any ambiguity. You want to avoid the causal confusion, so you want to make the reasoning traces causally related to what is actually happening. In a nutshell, we had to decide in building such an auto-labeling engine what to include in a chain of thought auto-labeling pipeline in terms of what are the critical components that really matter as opposed to irrelevant details, and what are the decisions that should really be highlighted. And second of all, how to anchor the chain of thought process. So what are the key decision moments with respect to which we want to generate a reasoning trace? Like, for example, here there is an interesting case whereby the car is turning left, and there is another car at the intersection that is yielding because there was a pedestrian that was crossing. So it's a little bit of a complicated situation, but here you want the reasoning trace to only focus on what matters. Not the fact that it's a tree, but the fact that there is a traffic light that is green, that there is a pedestrian crossing the road, and so on and so forth. And this will be the corresponding reasoning trace. So to handle this complexity, we have built a hierarchical chain of thought auto-labeling pipeline that comprises of many different steps. First of all, we use rule-based mechanisms to label initial meta actions. So these are high-level actions such as turn left or go straight that allow us to have a first-order understanding of a scene. Then we go into a data curation phase where we use, again, relatively heuristic methods to decide on the keyframe, the moment with respect to which we want to anchor the generation of the reasoning trace. Then we bring in large vision language models to ground the generation process into the visual, perceptual context and produce the initial version of a reasoning trace. Then we bring in a large reasoning model, something like, for example, to improve further the expressiveness of the reasoning trace. And then we use a mix of aspect models to summarize the reasoning trace into something discrete that can be used for downstream training. So all of this to say that building these auto-labeling pipelines is very complex and require the careful combinations of different models. Many of them are actually foundation models. So we're using foundation models to build a reasoning vision language action model. We're currently auto-labeling the majority of the data auto-lake at data lake with fairly high quality. And what the quality by now is good enough for large pre-training. We still want to have a very high quality reasoning traces for further fine-tuning and for that we use a more heavy strategy where we still need humans at different places in the auto-labeling pipeline. For example, one part that is sometimes is the selection of frame for anchoring generation of the reasoning trace. So for the higher quality data set, we use a human as a second check. We also use human to check on the critical components and the decision. And then we also have a final check on the final reasoning traces. So let me give you some example of what is the final output. So here there is a video of a scene. We pass it through our chain of thought auto-labeling pipeline. As a first step, we extract the most important aspects of the scene. So that will be the first 3 boxes that ends with a VLM. We see that we have 4 vehicles. One of them is particularly interesting because it's performing a cut-in maneuver. And then we go into the reasoning phase, whereby now the model outputs the chain of thought reasoning trace along with the corresponding meta actions in terms of both longitudinal and lateral control. And these are eventually the signals that we can use for training. Does it work? Does it help? The answer is yes. So this is one of the plots I'm actually most proud of from my research this year, is that we showed conclusively that actually training on a chain of thought reasoning traces helps. So beyond the buzz, actually, there is a strong technical grounding. So first of all, we see that when using chain of thought auto-level reasoning traces at training time, we do improve performance. That's what the plot on the right is saying. So again, on the y-axis, we have a metric that judges performance, the details of which are not too important. We compare the baseline without chain of thought training, and then a model with the addition of a chain of thought training. As you see, when we evaluate performance of 75,000 nominal scenarios, we see some improvement. There's no humongous improvement, but this is expected. most driving is actually boring, so you just go straight. So no matter how careful you reason about it, you still have to go straight. So you don't expect a lot of improvement there. The interesting part happens in the plot on the left, where now we have curated 300 very challenging scenarios, construction zone scenarios with visual auto distribution events and so on and so forth. And then you see that by training with the chain of thought data, you have a significant improvement in performance. And also qualitatively, I don't have here the time to show you some qualitative behaviors, but qualitatively you see that the vehicle performs quite different. It's much more contextual aware. And we can run this in real time. So this is basically a reason vision language action model that is outputting a real-time chain of thought reasoning traces on a live driving feed. Now, so far I've talked about leveraging, well, actually building data generation pipelines for reasoning traces. Of course, we can use foundation models to generate data for many other different modalities or use cases, such as scenario generation, behavior generation, sensor generation. For example, we have done work on using large language models to build new scenarios for stress testing and validation. Interestingly, with a large language model interface, we can also use an outside source of information, such as all the crash data that have been recorded by NHTSA to recreate new scenarios and fuzzy those scenarios. Ken mentioned Cosmos. Cosmos, of course, can be used to generate synthetic data by changing lighting condition, adding assets, and so on. And we actually show that the KPIs improve by training on synthetic data. And of course, foundation models help not just with data generation, but also with other tasks that are part of a data flywheel, such as data curation and data evaluation. And here I would like to highlight the work of Chris, one of the workshop organizers that will be presented during this conference on finding ways to attribute the performance of the model to the specific data mixture through the use of inference functions to better inform retraining or data selection. Or, and this is also a point that Ken mentioned before, we can use the foundation models for evaluation. And in particular, at least in the world of autonomous driving, we are interested in safety evaluation. Of course, the most basic version of safety is trivial, you don't want to collide. But safety is a much more nuanced concept. Like for example, do you want your car to be more or less aggressive or merging? And then for that, you have to reason about possible safety consequences. So for that, having a foundation model that helps with evaluation rather than just having legions of humans leveling your data is a significant accelerator. So I will stop it here, and I'll be happy to answer any questions that you might have.
A couple questions. Thanks so much for explaining how reasoning models can improve safety. But my question is it fast enough to guarantee reactiveness of the car against scenarios on the road? How fast should inference be? How fast should contextual reasoning be to guarantee reactiveness? Because at the end, it's not just control. They have 1,000 hertz, 500 hertz, probably 10 hertz.
Yeah, it is 10 hertz.
Yeah.
I mean, but back to Ken's point is, of course, you have a number of downstream models. This one, very classically architected. So basically QP-based, quadratic programming based, where you get the additional. But besides that point, of course, how quickly you can decode language tokens is a crucial question. I show you a case actually to generation. We do, but in order to do that, we use a concise language. So that's why it's very important that when you generate those reasoning traces are concise enough, not just because you want to capture the critical components, but you want to avoid excessively verbose explanation because that might slow down the computation times. Second of all, I showed you an extreme case where we are generating a reasoning trace at each replanning cycle. You don't need that. You don't need to output that necessarily at 10 hertz. You can be smarter and actually do that at a slower frequency. Third of all, there are a number of techniques such as, for example, parallel decoding and others that allow you to decode many more tokens per second with a relatively low degradation in performance. Fourth, and here we're more in speculative and research mode, there are new architectures, for example, diffusion language models that I think are very useful for reasoning applications because allow you to generate in parallel multiple reasoning traces, and they can allow you to do one of the things that from a decision-making background is probably one of the most exciting parts of reasoning, which is that of counterfactual reasoning. So basically do branching at the level of reasoning traces to think, okay, if the pedestrian were to do this, what? So I mean, it's research, but in the space of, so nothing new, but in the space of reasoning as opposed to just physical trajectories. So excellent questions. The bottom line is that we have a lot of tools at our disposal to tackle it. Thank you.
We're going to resume at 11 a.m.
It should be pretty straightforward. Hey, I got an email with the bio.
We're gonna set it up right now.
Yeah.
Sounds awesome.
Thank you.
You work with Doors?
I work with Dorsa.
Go shoot the doors.
Yes, I'm the connection here.
Well, I mean, she's when I first started talking to her, she was my first wife.
Oh, really? Oh, that's awesome. Yeah. But she's done really well.
Someone, you could maybe say this like
Sid, yeah. Sid was a little earlier than me, so definitely him. Maybe some of my early stuff.
Extensions, but all of her students have like funding.
Yeah. I mean, yeah, I had funding. I actually had DoD funding when I did my tuition.
What was it from?
IndySeg.
And what?
IndySeg? It's like the
Oh,
National Defense.
Yeah. That's pretty good. Yeah. I got the NSF back way back. This is just
Yeah.
was there like a DoD sponsor, like a company that worked that?
There is ordering on the website, right?
Yes.
On the spotlight.
Yeah.
And then like, so, you know, yeah, I guess that's the reason why. Everybody's likely to share their at some point based on their email.
We're gonna do that now. So the spotlights, don't worry, just check your email in a second. Yeah.
But more about algorithmic innovation section, like that could be algorithmic innovation section that you run and transfer of data. Yeah.
It's working. Yeah.
I wanna get it some from that.
Posters, posters.
Oh, yeah. This is a lot. It's like the criteria, LLM space. What about? It's like zero. Yeah. Throwing off robots. Building the pad, but yeah, like videos of things or other things. Track this phenomenon, merging this alignment. No, I. Fine tune elements. What is and same like just just unrelated. I guess we need to internalize it. Yeah, that's what it is. Yeah, that's what we want.
I'm gonna try and make sure that this is.
Yes, I'm gonna remove some things.
We'll see you soon. What is, it says it's still pending?
There's this.
Oh, nice. Oh, so it's working.
Can you check on your laptop?
Yeah, let
Oh,
me.
you got a better use of the Zoom, huh?
So the Zoom feeds to YouTube live stream.
Yeah.
Yeah.
That's.
Let me try sharing my screen with Matthew's slides. You sent us an email, right?
Chris, yeah, so UN in Israel.
Here it is.
That one.
Yes. Yeah, we can try setting up Matthew's slides. Hopefully it will.
Should work, right?
It should just work, yeah.
I'm so hungry, man.
Same.
So far, it's been going all right.
Yeah, I think it's been decently smooth.
Okay, so now what, let's say I have to share my screen now,
Yeah.
right? So let's go like, let's move those slides. Or no. Let's just share.
Yeah. Should share desktop too.
Do like this, because
Yeah, it will, yeah, that works. If you just share desktop too. Cool.
how's that?
Fine, just make sure. All right. Yeah, looks pretty clean.
Yeah, okay,
But
let's,
how come that's not coming through?
I think it's, there's some lag.
Yeah.
Thanks, Matthew. This is only, yeah, see. There's just lag. Yeah, see, and now it's you flipping through it. Okay, I'm gonna add this link to the website.
Where's the dongle?
One sec. Joey, you're gonna have to check again.
Okay.
Data is too boring. Instead, we collect a large egocentric human task-oriented dataset. Here, task-oriented means the human data has clear start, end, and focus on specific tasks, just like robot data. We
What dongle?
advocate human-centric representation, which represents actions.
That doesn't work.
And
They said it doesn't work.
it's an embodied nothing representation that applies to any.
I don't see a USB on this. It's a Mac. What are you trying to connect? Is that audio?
Yes,
Oh.
this is the main audio cable.
That must be, that needs a dongle. That needs a USB-C dongle, it looks like.
Ah, there is. Ah, and that's all. The
That's
remote
that's
living,
great.
and
Maybe one of the organizers has a USB-C dongle.
I gotta find it.
They wanna, you have a dongle for that? USB-C?
I do, but it didn't work earlier,
Oh,
so
fun.
we have a backup.
This is for projecting the audio for that video you got.
But we'll
Worst
make
case,
it,
you could have the speakers run and then just the microphone pointing at the speaker.
but then you get the feedback.
You do?
Yeah, you'll get the
Really?
feedback from.
Yeah, that's true. Yeah, I didn't realize that.
Yeah.
Feedback does not sound, that would ruin everything. today.
Yeah, I don't think so. But I think it'll all work out, so. We might start like 2-3 minutes. That's all right, yeah.
So let's say hi.
Good to see you, man.
going?
How are you?
Good. How's the workshop?
It's coming along. A
Yeah.
lot of hiccups because of the AV system's a little bit difficult to get working. But yeah, but we're hanging in there. Hey, we should get dinner or something, eh?
Yeah, let's
Yeah.
do it. Let's do it.
Yeah,
I
I've been-
have your contact.
Yeah. When did you, I don't have WhatsApp. Do you have my iMessage?
Yeah, yeah.
Good. Yeah. When did you get in?
Yesterday evening. I'm extremely jet lagged.
Okay.
I barely slept.
Okay.
But anyway, I won't get to it.
Yeah, we're gonna get started here. Yeah.
Yeah.
Okay, man. We'll see you.
You introducing
Jules. Oh, it's me. It is me. It's me.
If there is no way to play audio from your laptop in the room, then that's how it is, right? There's nothing.
I think this is gonna work fine. What was I gonna do for the? Okay, the other lightning talks are fine because they're all muted anyways. We're good. We're good. Yeah.
If one of you manages the spotlights and all you do is between spotlights, like say, you just call up the next person, right?
We only have the
Yeah.
titles of the paper. We'll just say
Yeah.
the next paper is, yeah.
Yeah, you just call them up and help them set up and manage a question in between.
Yeah.
For the last one, between the second to last and the last one, tell all the lightning talks to start lining up over there.
Is lightning talks? Is that right after Matthew Stable?
We should probably go ahead and get started.
But it's Matthew's talk, spotlights, lightning exposures.
Yes, exactly.
So
But
during,
if
for the last spotlight, just start telling people to line up in the order that you sent it out already. And they'll walk up on the stage, present, and walk off.
yeah, but if they cannot join the Zoom, that's a bit of a problem.
Wait, why, who needs to join the Zoom?
The lightning talk,
The spotlight presenters,
I just sent an email to all of them.
but they're not the people that are necessarily presenting. So I need to find those people.
I think one of them just came up to me and I sent him the link for today. So DataMill's covered.
DataMill's covered.
DataMill's covered.
You sent to
I
GFA
sent to Jaffe.
Uh-huh.
Momo Ads is covered.
and Wolf,
I
Boye,
sent- I
you
sent-
sent to Boye? Yeah,
Yeah,
probably
it's
it's the,
here.
it's the main, and then Nerf Og is this guy named Daniel Ekbo.
Okay, let's go find him.
Yeah. Oh, it's okay, it's okay.
It's okay?
Yeah, we have it figured out.
audio?
Yeah. Should be okay. Yeah, thank you. Okay, everyone, we're gonna get started. Before the first talk, if you're a spotlight presenter, could you please come to the first row? Thanks. All right, so we have a talk. We're here joined by Matthew Marge. Matthew Marge is a DARPA program manager as of January 2023. He joined to create, execute, and transition programs in artificial intelligence, human-machine interaction, and multi-agent systems. He's an adjunct professor of linguistics and computer science at Georgetown University with over 50 authored or co-authored publications. Matthew, please take it away.
Thanks so much, Chris. Thanks for Joey for hosting. So everyone, good morning to you all. I'm here to talk a little about one of my new program efforts at DARPA that's looking to create new investments in AI. And I'm here to actually, my goal in the next 15 minutes is just to get your feedback and thoughts on potential challenges we'd like to identify for this new effort that's called AI Forge. And I'll spend a few minutes talking a little bit about DARPA and then get into a little bit more details about this, the new initiative I'm leading called AI Forge at DARPA. So many of you have heard of DARPA before. It's part of the Department of Defense in the US government. Our main mission is to create and prevent technological surprise. It was originally created in the 1950s in response to the launch of the Sputnik satellite. You can see some pictures here of DARPA's greatest hits. You see in the middle, the DARPA, DARPA Urban Challenge, DARPA Grand Challenges back in the 2000s, 2010s. And then, the DRC, DARPA Robotics Challenge, mid-2010s that did a lot of humanoid robotics. So as I meant, our focus is on creating breakthrough and paradigm shifting solutions in technology. That's our kind of space in the research and development ecosystem. And we work at the highest levels of risk tolerance in the US government. So we're looking at trying to tackle the highest risk, high reward challenges and solutions. And looking to create disruption and in terms of the investments in fundamental research, what are the disruptions needed to change the field of whatever technology we're targeting? So in the case of robotics, there's a lot of mainstream focus and interaction on foundation models. So what are the opportunities for disruption? So what are the focus areas that have implications for national security, for example? And there's 6 technology offices at DARPA. I'm part of the Information Innovation Office, where we lead mainly the work in AI and cyber. So you see there are 4 main thrust areas on transformative AI, offensive, defensive, cyber, fighting in the information domain, and resilient, adaptive, and secure systems. And I'm part of the cohort of the AI program managers at DARPA, where I create and manage programs that are multi-million-dollar investments in AI. So now I'll take a moment to shift gears, talk a little about AI Forge as a program. So this initiative is something that I developed over the course of the last year and a half, really to explore ways that we can create breakthroughs in AI for national security by creating basically a forum, an industry, university, and government forum, where we want to partner with a lot of the frontier AI labs you hear about in the news, all the big companies, in ways to kind of cost share in that. And it's also a partnership with the National Science Foundation, so I'll talk a little about it. So here's our main, structure on AI Forge, a little bit about the program. So the basic premise is to stand up an industry, university, government forum to create breakthroughs for national security. And AI Forge is strategically aligned with the AI Action Plan. You might have heard about the AI Action Plan from US government and the Office of Science and Technology Policy. We're partnering on this effort with the US National Science Foundation, not only as a co-sponsor, but also an operational partner that can take over the responsibility of running this forum once it reaches a steady state in a few years. We want ultimately in this forum to combine the talent from universities with the capabilities and resources from the frontier AI labs to create national security focused AI innovation. And also ultimately to create an ecosystem that catalyzes innovations in AI for national security and fosters talent and idea exchange more freely between the frontier AI labs, government, and universities than today. So I'd like to talk with you today a little about the structure of this program and get your thoughts on what you think could be good ideas. And this is where I want to open up for questions and comments on what kind of challenges you see in the field of robotics, and especially in this workshop on data collection. What are the implications and challenges we should prioritize internally with this kind of effort? So the centerpiece for AI Forge is to bring on a nonprofit to serve as a forum manager. That's what's in the middle of the slide here. And the AI Forge forum manager will execute and manage a series of what are called project ventures, which are high risk and fast-paced university-led efforts that are basically a year or less in duration, trying to tackle a challenge at scale. In this case, each project venture, we're going to be launching dozens of these project ventures, but each one is meant to tackle a critical AI challenge for national security. And this is where I want to get your input today on what do you think should be critical challenges. And within the AI Action Plan, this program is essentially aligned with the effort to advance research in AI interpretability, AI control, and adversarial robustness. So I think one thing I'd like to bring up in terms of when you think about topic areas and themes, what advances those three areas for AI, especially robotics and AI. And each of these kind of critical, each project venture is supposed to tackle a kind of a shared or cross-cutting problem across the industry. And we want to tackle ultimately what we consider pre-competitive or pre-commercial AI research in this program. And each project venture is trying to tackle things at high scale, meaning demanding high compute or use of frontier models. So many universities today have trouble getting access to the level of scale that the frontier labs have in terms of either compute or frontier models, and we want to enable that to be possible in this program for universities. So let me talk you through some of the pieces of this program in terms of the elements. So universities bring the core talent to this forum, ultimately in the form of faculty, grad students, and postdocs, being able to now do things at scale with the resources we want to with resources that we plan to have being offered by the frontier labs. And the frontier labs, we're talking to all the major players here in forming this forum, are looking to provide insights into critical AI challenges based on their own internal forecasting. Ideally, liaisons from those companies can be partnering with some of these project ventures and offering up resources in the form of frontier model credits and compute. And for national security stakeholders, we're thinking, folks across the government that would want to be tracking these kind of project ventures in the US government, offering up insights into national security challenges to shape project ventures and use cases, along with operationally relevant data. And in addition to that, universities are now being, with this forum, it's about enabling them to tackle a lot of things at scale. With the frontier labs, it's about incentives like accessing shared intellectual property or shared IP and early access technology. And then for national security stakeholders, it's about getting access to demos and prototypes. So let me just kind of reflect a bit more. This is the only slide I really have in
in this presentation. I want to have a little bit of time for discussion, but my main question for you all is sort of, what do you think are some of the critical challenges in robotics that are focusing on AI interpretability and AI control or adversarial robustness? So yeah, and I can also take questions about the program itself. So let me stop there and take questions. Thanks very much. Yeah. Yeah, so my contact information is, you can find my email address there. All right, thanks very much, everyone.
All right, everyone, now we're going to start the spotlight talks. So we have 4 spotlight talks. The first is from Wolf, which is about captioning with advanced captioning with the world's fundamental framework. So we'll have 4 spotlight talks, and then all the lightning talks will begin right after that. So if you're giving a lightning talk, towards the end, we'll give you another reminder that you can line up in order that we then have. Thanks so much, and we'll start the spotlight talk.
Okay, hi everyone. It's my great honor to give a presentation about our work, WOF. So as we all know, for robot learning, the auto labeling is a very critical task for us to do. How we annotate good data is a really important thing. So this work, we aim to try to understand from video and caption everything that we can learn from the video and use that to build the labels for any robot videos. So that's our name, captioning everything with a word summarization framework. So as you can see from this is a video, autonomous driving videos, and we basically want to annotate what is happening and how the car moves. And so the reason we propose the work. In summary, it's a mixture of experts that will take the usage of both video level model and image level model to annotate the car's movement as well as the scenario description. So here is a WOF example. And the WOF not only can provide annotations for autonomous driving, but it could also for robotics and the general things. To evaluate this, we also create a benchmark to evaluate all these scenarios. And we also design a cap score to base the evaluation matrix to evaluate how the annotated labels aligns with the real world videos. And we also conduct regulation study to evaluate the validity of the cap score with the human evaluation score. And in summary, WOF achieves much better results based on this mixture of expert framework. It outperforms GPT-4V and Gemini Pro 1.5 in this motion captioning. And here we give another example. And this is our WOF's caption, and you can see it can successfully capture the car's motion as well as the scenario. And in summary, we designed the first word summarization work framework WOF for video captioning, and also the based metric cap score. And we also introduced both benchmark and 4 human annotated benchmark data set. And the code data and the leaderboard has been open source recently, and we will continue the efforts and improvements to refine the WOF data set. And just now I talked about the Wolf V1, which is the submission for this workshop. But now through this opportunity, this is our first time to announce our Wolf V2. Basically, we propose a very advanced, I believe it's a soul tower model that to annotate the motion information in any robot videos. So for example, this is all the results here are zero shot. So basically, we just randomly take any robot videos, and our model is able to annotate each object as well as how each object moves. And also, we automatically capture what object, what hand is moving, and then we track that object and describe and also annotate the semantic information with the movement. And all these things are zero shot. And the technical detail will be released soon, but in general, our model is trained on basically the general videos. It's not specifically for robot videos, but it can be generalized very well to robotics. So thank you very much. More information and the leaderboard will be updated. Thank you.
Thanks so much for the great talk. We have time for one question, actually, if anyone has a question they'd like to ask. Otherwise, I would ask, how do you determine which objects are relevant for manipulation within the scene?
Yeah, so basically for the demo is a show. Basically, we automatically detect what object is moving. How we detect that is based on the object's movements. We track the location of each object in every frame, and then we can identify whether the object is moving. If the object is moving, then we will start to track that object and to identify that movement.
Thank you so much.
Thank you very, very pleasure.
Our next spotlight will be on Momo Ads.
Oh, okay. Yeah, hi everyone. My name is Jiafei from Allen Institute of AI and also University of Washington. Today I'll be presenting Momo Ads. So I think we have seen a huge success with open data model, especially coming out from, I'm not sure why is it weird. Does this work? Okay. Yeah, coming out from AI tool with Momo, and Momo has sort of pushed the boundary of pointing capability, developing frontier models, and you have seen that many of these frontier models start to develop pointing capability. In fact, this is really useful in robotics, for example, providing good priors for automating robotics foundation models. But the question is, can such spatial representation go beyond pick and place? Can you tell Momo to generate a plan, a trajectory plan to sort of steer the policy to be able to execute this task or pour me a cup of tea? And beyond that, we need to have some sense of depth to be able to reason over our action. Maybe I just share this. And is reasoning over action via language actually sufficient to solve the task? Giving GPT-5 this task and this instruction, you're not able to get a prompt that's able to solve this task. And with that, we introduce Momo Ads. So Momo is an autoregressive model that's able to take in observation and language instructions, perceive it, and generate perception token in a way that when it's decoded, it's able to represent in this kind of depth map. And condition on that, we generate visual reasoning traits, sort of act as an intermediate plan for the robot to take on. And when you decode this, you actually get a visual sketch of the next time step of what the robot actually wants to do. And condition on all this, you're able to actually output the necessary robot control action in order to solve the task. And from our pre-training evaluation of Momo, we are able to sort of achieve some of the state-of-the-art performance on simple benchmark, which reflects the distribution of the OXE dataset. And in fact, we are actually able to achieve this with much lesser data as compared to the other models from physical intelligence and also from NVIDIA groups. So the secret comes in the data, similar to this workshop. We decided to use open source data, but their quality and quantity are just not good enough. So for just some context, you can see this kind of data, say OpenX embodiment, with real instructions, even for like a whole 9 seconds, the robot is not moving at all, or even the robot doing random things. And this is not the kind of data you want to use for training. So we started by actually filtering the entire OXE data set coming down to only 3 data set with over 190,000 trajectories. And beyond that, we collected our own high-quality mid-training data set called Momo Ads data set. This contains different tasks in different household settings, even autonomic skills. For example, how do you place a plate in an upright position, and also non-prehensive skills. The key idea of Momo Ads data set is focusing on high-quality demonstrations with repeatability. So each of these 100 tasks has over 100 demonstrations. And even by doing this, we are still far away from large-scale robotics foundation model that is training on a huge amount of robotic episodes. So how do we bridge the gap? So in LLMs, they use intermediate chain of thoughts to do reasoning, but reasoning in language is ambiguous for motion space. So Momo proposed a new idea of robots should be able to do reasoning in space. And the way we do it is by curating data in a specific way to generate this action chain of thoughts that can be grounded. So we use Momo to generate all the points, and connecting all these points, you'll get a trajectory of what the next time step the robot should take. And beyond that, you want to reason beyond just 2D pixel, but a lot of this data doesn't have 3D. So we have to have somehow implicit 3D. So we use this idea of perception token to actually decode and label the RGBD image with this perception token that represents depth. And putting all this together in an autoregressive way, you get the action reasoning data set that sort of empowers Momo's reasoning capability. And we also incorporated other kind of data set to have the general vision reasoning capability. And Momo has 3 stages of training: pre-training, mid-training, and also post-training for different applications. And we're able to do reasoning in space, which outputs action, or we're also able to steer Momo in a way. And for post-training evaluation, Momo, as compared to all the other autoregressive models, we achieve state-of-the-art performance and also compared to reasoning-based models. And beyond that, we're also able to show that Momo is able to generalize to many downstream applications, real-world tasks across different embodiment. And okay, oh, sorry. Okay. What? Okay. But anyway, let me say I can go over this. Oh, I might not be able to expand. But anyway, yeah, thanks for everyone. I think hopefully feel free to ask me any questions.
So much. We have one question if anyone has one. No, just no questions. I wonder how estimating errors is sort of like the point detection or the depth estimation like impacts the model.
Yeah, so I think definitely those will affect the model, but because we are focusing on large scale pre-training, so a lot of these are counter and learned in an implicit manner by the huge amount of data. Obviously not that much, but yeah. Thank you.
All right, thank you. I guess talk will be on second.
Oh, okay.
Yeah.
Hi everyone, this is Satish, and today I'm presenting this exciting work, DataMill, on behalf of my colleagues at UT Austin. So recently, the robotics community has collected a lot of large data sets with varying embodiments, scenes, and tasks. Now, suppose you want to train a policy on a target task, and you want to use this data to improve the performance of these policies. So given the messy nature of this data, it's unclear which data would be actually helpful for a task. Some samples would be helpful, while others could be harmful as well. So how do we select the right subset for improving policy performance? So prior works tackled this problem by selecting most similar data from as the target data set based on some heuristic measures such as motion similarity or visual similarity. While intuitive, this can bring data which could hurt the policy, and it could also miss out on valuable data which could be helpful to the policy. In reality, what we want is this weird purple blob, or more accurately, what we want is to find a subset from the data that maximizes the performance of the policy on the target task of interest. So given this intuition, let's make it more formal. given a data set B, a learning algorithm A that maps data to a trained policy and a performance metric, which in our case is the success rate of policy rollouts. We want to obtain the data, the subset of the data that maximizes this performance metric. So directly optimizing for this objective is hard because it requires you to train policies for every possible subset of your data set. So in order to solve this issue, we use the data models framework. Now, what are data models? At a high level, data models try to approximate the metric as a function of the data. Under the hood, what these methods do is they try to measure the positive or negative influence of each sample on the performance metric. Thus, it's directly allowing us to measure the usefulness of a data point. So I won't get into how we learn this, learn these data models. You can check the paper for that. But two key things to know is that there are estimators which require several passes over the true performance metric. And the second key thing to know here is that it's much more efficient to obtain data models than training policies on every possible subset of the data set. So in order to adapt the data models framework to robotics, we introduced several key challenges. The first one is recall that data models require computing several times the true policy of the true performance metric, which in the case of robotics would mean costly rollouts, which is not feasible. Therefore, we use a proxy metric of validation loss on held out target data instead. Further, we also use sub-trajectories instead of using single data points to make the estimation of data models less noisy. And we also introduce a co-training recipe, and I'll not get into the details of those two in the interest of time. We evaluate DataMill on the challenging setting of data selection from the messy OpenX embodiment dataset. And one of the key results that I want to highlight here is this result on cross-embodiment transfer. So here the target data that you can see on the right is with a Tiago robot, and the Tiago robot is not at all part of the OXE dataset. So this is a completely new embodiment, and we find that even in this case, the DataMill framework can allow us to select relevant data. And this shows that the true finding this data selection problem is much more nuanced than just doing visual similarity or motion similarity, because you can use data from very different sources as well, and it leads to positive transfer. We also evaluate on multiple target tasks together, and we find that in all cases, DataMill outperforms prior methods which are based on heuristics. In summary, we introduce a data model framework, which is a more principled way of viewing data selection. And in DataMill, we introduce several key adaptations which make the data models framework work for robotics. Finally, we show across real world and simulated tasks that DataMill outperforms prior heuristic-based methods. That's all.
We have time for one question. Okay, if not, I have a question. So in DataMill, you're using the validation loss as a sort of attribution target for selecting data.
Yeah.
The validation loss is sort of surrogate for the closer performance of your policy. I'm wondering if there are some quantitative trade-offs between doing attribution on actual rollouts versus the validation loss.
Yeah, this is sort of the question that we expected, right? Because a lot of critics on whether validation loss is a good metric. So we actually do evaluate and do experiments in our paper where we start with actual rollouts, and we compare the performance difference between using the proxy measure of the validation loss versus using the true real world rollouts, and we find that the performance drop is very small in this case. So it appears in our case, in the data selection case, it seems like a good enough metric.
Thank you very much.
Thank you.
All right, hi everyone. My name is Daniel, and I will be presenting in behalf of the authors. NERV is a novel approach to augmenting existing robotic models to work on novel objects using neural radiance fields. In imitation learning, an expert controls the robot to perform a task, creating demonstration to train a network to mimic those actions. And this works, okay, yeah. This worked for the original task, but often fails to generalize to new objects. While collecting more demonstrations for each new object might help, it is not feasible at scale. Existing methods use pre-trained diffusion models to augment the training dataset by inpainting a new object in the position of the old one. However, this approach has some limitations. They inpaint objects with the wrong size or orientation, produce frame inconsistencies, and are slow due to iterative denoising. We instead use NERV models, which are faster, more photorealistic, consistent across frames, and support a wider range of viewpoints. Our method has 5 steps. First, we build a NERV of the new object. Second, we compute camera poses for each frame. Third, we use the NERV model to render the new object views. Fourth, we erase the old object with an inpainter. And finally, we blend the NERV renders with the original video frames. This slide has an overview of the method shown. And the animations following demonstrate the steps. First, we segment the original object using a video segmentation model. And second, we erase the original object of interaction. Third, we use a robot gripper to create a NERV model of an object we want demonstrations from. Fourth, we use a trained NERV model to render the NERV object in the position of the old object. And finally, we combine NERV renders with the trajectory in images to make a highly photorealistic synthetic dataset. Here we show our method versus other methods when it comes to augmenting the same demonstration. We also show that our method can properly grasp the blue box while other methods are not able to do that. By generating highly realistic synthetic data, our method generalized to novel objects with high success rate. And even with having to train the NERV models, we still find that our method is able to augment data much faster than the baselines.
What if the objects are in clutter? Do you have trouble with the segmentation there?
That is a good question, and I believe in some cases, yes. I mean, the use of the shelf object detectors, like grounding dyno, etc. And so those are robust enough in some clutter situations. But if it's too cluttered, I think they would fail.
All right, thank you so much. Now I move on to the opening talks for all of the posters. So if you have one, please line up near the one on the right hand or left hand side of the stage. And Chris will be managing the video. So everyone with a lightning talk, please head up to row 1 and we'll get started with
Everybody else, they're professional. You're not all
Okay. All right, we should be good to start. Starting with demo speed up. Okay, click it when you're ready to start. And then
Okay.
click the video.
Okay. I'm Zhenrong from Tsinghua, and I'm glad to present demo speed up, accelerating visual model policies via entropy guided demonstration acceleration. Are you tired of robot videos with 5x acceleration rate? To make robot work like humans, we believe fast human speed execution is very important. Therefore, we propose demo speed up, a self-supervised method that allows you to train fast visual model policies from slow demonstrations. A key insight here is that not all the frames in a demonstration are as equally important for a task success. Frames with higher action entropy correspond to more casual sections and therefore can be more safely accelerated. Demo speedup can be applied to arbitrary generative policies such as popular ACT or diffusion policy. We found demo speedup can boost the execution speed by up to 3 times while maintaining or even boosting the task completion success rate. Thank you.
So hi, I'm Zifan from New York University. Excited to present our work, Touch Begins Where Vision Ends, shines with policies for contact-rich manipulation. So a lot of times, such as this, USB insertion is very difficult for robots because it requires millimeter-level scale precision. And that's the reason why we propose our vital visual tactile local policies that integrate egocentric vision and tactile sensing to achieve precise manipulation within just 3 demos of behavior cloning and 45 minutes of online reinforcement learning. And we can achieve different spatial generalization and also visualization to different kind of backgrounds and robust to different disruptors. As you can see, it's doing a precise insertion task here. Yes. And also we found that tactile is very important for all kinds of contact-rich tasks that is helpful for the manipulation. And here is the live demos for us doing the real robot routes. And if you are interested, feel free to visit our work on our website and check our code. Thank you very much.
This is not my.
Yeah. What number are you?
I'm 4 because there was a miss, I guess. I'm collage.
Let's skip this one then.
Hi everyone, I'm Satish and I'm back again, this time to present collage. So we want to train specialist policies without having to collect lots of new data. Data retrieval methods enable this by starting with a small scale target data set and finding from large scale data sets data that is similar to the target, and then they co-train with the target and retrieve demonstrations. However, current approaches for data retrievals rely on a single modality for retrieval, such as visual, 3D, or motion similarity. However, relying on a single modality can be limiting as different tasks benefit from different types of cues. In collage, instead of committing to one set, we retrieve data using different modalities and then predict a weight for each modality based on its relevance to the target task. I know there was a lot of details in the slide that I didn't cover. If you want to know more, please visit me at the poster. We achieve around 57% performance improvement with collage and on real world tasks. Thank you.
Hi everyone, I'm Lauri Suomala and this is a work titled Synthetic versus Real Training Data for Visual Navigation. Sim-to-real gap is a well-known issue in robot learning and several prior works try to quantify the width of this gap. A question that has remained unexplored until now is how the sim-trained policies compare to ones trained with real data. This work studies the issue in the context of topological navigation. We train a navigation policy on real data, another version of the same policy on simulated data, and we compare both policies on a real robot. And here you can see an example of a turtle bot navigating with the sim-trained policy. We find that with enough training data, the simulation trained policy can outperform the real data trained counterpart. and the previous SOTA render-to-real data. Vision encoders pre-trained with large-scale datasets and on-policy learning are crucial for the sim-trained policy's real-world performance. Thanks for listening, and see you at the poster. Okay, I'm Xidong from SaaStech, and we present the Magic Cloud. Okay, I'm Xidong from SaaStech, and we present Magic Cloud. Magic Cloud is a two-finger effector, and it can be handheld or mounted on a robot arm. It captures action data from real-world demonstrations, and the third finger can feel the force and 3D shape during the interaction. We use iOS app to provide 60 pose and RGB data. And all data can be visualized through a web-based interface. Human can use Magic Cloud to teleoperate a robot arm and can physically feel the force feedback. And we use Magic Cloud to collect data for multiple tasks, both single arm or dual arm. And we also use Magic Cloud in a simulation platform like RoboSwift. So that's all. Thank you.
Hi, I'm Daniel, and I'm presenting IVE. Humans are naturally curious. Through exploration, we learn about the world's dynamics. How can we get robots to explore autonomously without extrinsic rewards? VLMs can reason about what objects are, where they are, and what might happen next. However, when operating independently, they rely only on imagination and prediction. On the other hand, humans are motivated to discover new scenes. Driven by curiosity, we use semantic understanding, structured reasoning, memory, and action to explore. Inspired by this, we present Imagine, Verify, Execute, or IVE. IVE is an agentic system that helps VLMs explore more like humans. It represents a step toward more grounded and semantically guided learning for embodied agents. Thank you.
My name is Shizhe. I'll present our work, Guardian, detecting robot planning and execution errors with vision language models. Robots often fail. It's critical to detect these failures for recovery. The existing work mainly rely on limited data and single images, leading to poor generalization and low precision. So in this work, we propose a Guardian, a fine-tuned VLM for failure detection. It combines multi-view high-resolution images and language reasoning to improve the failure detection accuracy. We also propose an automatic failure data generation pipeline to train Guardian. We perturb successful robot trajectories in both simulation and real world to generate diverse failure cases, including planning and execution errors. Our model achieves state-of-the-art performance in both in-domain and out-of-domain benchmarks. For more information, please check our poster. Thank you.
Hello, my name is Archer Kremshin. I'll be presenting task robustness via relabeling vision action robot data. While robotics manipulation datasets remain small due to difficulty of collection, with language diversity especially lagging behind. This often leads to robot policies that can perform tasks in new scenes but struggle to follow language instructions, often defaulting to visual cues instead of the text commands. Our work, TREAD, systematically augments existing datasets with greater language action diversity without collecting new data. Using VLMs, we 1. Decompose tasks into semantic subtasks, 2. Identify temporal boundaries in the trajectory videos, and finally, generate grounded paraphrases incorporating object attributes and the spatial relationships. We test on 2 scenarios, language generalization with linguistically modified tasks and motion generalization with new instruction scene pairs. The results show TREAD improves both planning generalization and language following, achieving gains without any additional robot data collection. Thank you.
Hello, everyone. I'm Amir. I'm presenting our latest work for data generation. Our NICE framework is a generative model or generative pipeline that performs the different manipulations on existing samples. And it can basically scale the data without any human involvement. We done a number of experiments to show the resulted data is very realistic comparing to real world collected data. And also we show that fine-tuning our data can significantly improve affordance prediction, and as well as the manipulation tasks when we is evaluated under different cluttered environments, and it can improve the robustness and generalizability as a result. Thank you very much. If you're interested, drop by the poster.
Okay, just let me make it easier.
We present GRIM, a framework for task-oriented grasping. GRIM's full form is Grasp Realignment via Iterative Matching. There are a lot of grasping data to learn from, but only a fraction is task-oriented. This requires for a data-efficient method to learn generalizable grasping that generalize over tasks and objects. To tackle this problem, we present GRIM, a training-free framework that conditions grasping on generated videos. We first use reference, image, and desired task to generate a video of desired grasp, then reconstruct the hand-object interaction, saving this hand-object interaction into a flexible memory. During testing, we exploit this memory, but to retrieve similar objects and align it with the scene, we efficiently transfer the graspers. Although we demonstrate real robot application on paddle gripper, our approach is easily adaptable to dexterous hands. To find out more about them, you can scan the QR code. Thank you.
Hi guys, in this work we present two-handed afforder for learning precise, actionable bimanual affordances from human videos. Most affordance prediction methods typically reduce the problem to part segmentation or direct object segmentation. Instead, we propose a pipeline to extract these task-oriented affordances directly from human video sequences. We use mask propagation and so on, and we get a data set to which we train VLM-based segmentation in order to get both bimanual segmentation masks for the left and right in a task-oriented manner. And we see that our work works better than a bunch of the other baselines that are there, which do either full object part segmentation or aren't able to localize the object properly. And with this, we're actually able to use more actionable grasps that robots can execute based on the task that they need to perform. Thank you.
Hi guys, I'm Jiwon from Hyundai, and I'm here to introduce a way to scale your dataset without robots. We create dataset directly using hands with a VR device. So first, we start by locating a robot base in the VR coordinate frame. This is used to transform hand trajectories into robot end effectors. Next, a human naturally performs a task. And then we add gripper state and action to the collected dataset using VLM and multimodal filtering. And then to address the visual gap, we replace human hands with robotic hands in the observations. To verify our dataset, we use a custom dual system VLA, and the results show that faster data collection and boosted policy performance. Future works will focus on minimizing the domain gaps. Thank you.
Hello, everyone. I'm Greg Wolfe from Zoox, and I'm going to be telling you about a reward-driven method for scoring agents by relevance to autonomous driving. Humans are very effective at focusing on what matters in a scene and ignoring irrelevant information. We'd like our robots to do the same. In this work, we use a pre-trained driving policy, a driving simulator, and a driving reward function. And then, instead of training a new actor to drive, we train an actor that seeks to mask out as much of the driving policy's input as possible. And then we can leverage the existing driving rewards to find the maximal set of inputs that we can remove while still getting good driving behavior. If an agent is not required to drive well, then that agent is not relevant to the driving task. In these examples, we can see agents marked with these colored dots are considered relevant, with the reddest dots being the most relevant. Yeah. Please come by our poster or read our paper to see more quantitative analysis. Thank you, everyone.
Hi, I'm Ichi. I'm going to present Caesar, a self-supervised approach to data curation for large-scale imitation learning. So robotic datasets are growing fast in the size, and such large-size datasets always contain bad quality data like suboptimal and redundant data. How can we curate the datasets to effectively enhance policy performance? We introduced Caesar, which first starts from the diverse data trajectories, and it can detect the suboptimal and redundant transitions, and then it creates the data to create a curated dataset. We then train like VLA models like Octavine and get better policies. So we apply the method to different like large size data sets like OpenX or Cirrus, and then we shows that it can like outperform other data curation baselines. We compare it with Uniform, with DemInf and Remix, and we show that ours is getting better policy success rate. And this is a demonstration about like real world rollouts on the Mutex dataset. And thank you.
Hi, I'm Haruki Abe from University Tokyo, and our research focusing on expanding the robot dataset by combining two approaches, cross-embodiment learning and offline reinforcement learning. Cross-embodiment learning means training a single model across a robot with different morphologies, and offline reinforcement learning, compared to the imitation learning, allows us to learn not only from optimal trajectory, but also suboptimal ones. By combining these two methods, we can train across a wide variety of robots while also use suboptimal data. This gives us the potential to significantly scale up the dataset. In our work, we analyze the advantage of this setting as well as the challenges it introduces. If you are interested, please come and check out our poster. Thank you.
Hi, my name is Bo. In this work, we study embodiment scaling laws. Embodiment variations are pervasive in the real world, and we want to understand how to learn from and generalize across diverse physical embodiments. We use our hypothesis is embodiment scaling laws, that training policies on more embodiments lead to better generalization to unseen ones. We use robot local motion as a testbed and generate 1,000 robotic embodiments by varying geometry, topology, as well as joint-level kinematic constraints. We then train a single model capable of handling diverse observation and action spaces on random subsets and observed positive scaling patterns in terms of generalization performance. In particular, we noticed that scaling embodiments is much more effective than scaling data to enable embodiment level generalization. Our single best policy can be deployed on go-to robots with modified joint limits, as well as humanoid H1 in the real world without additional training. We hope this work in local motion to inspire progress in other task domains. Thank you.
Okay, our role contrastive learning in contrastive in context learning with active memory for task planning focuses on LLM-based task plan. This is our proposed framework. From the environment, we can obtain task instruction. Then the LLM planner generates demonstrations. When the robot executes them, the outcomes are divided into successful or failures. These are selectively updated into active memory with our diversity of selector. The successful demonstrations are used as positive prompting to imitate the ideal behaviors, and failure demonstrations are used as negative prompting to recognize incorrect behaviors. In this way, the model can learn by exploiting the contrast between these two types of promptings. Thank you, and see you in my post session.
Hello. My name is Pencheng, and I'm from National Research Council of Canada. So here we are presenting this work on data modalities. Data drives robot learning, however, it's unclear how to structure good data. We study teleoperational modality and evaluate key components. So we do 2 tasks, wiping a table and turning on a lamp with 400 demos from Oculus VR, and happily in verse 3, we evaluate via the NASA workload and fine tune on the GRP like the Octo model. So in comparison, we found that VR controllers physically and mentally easier, but it's less precise and more frustrating. The haptic controller is more difficult, but precise, which yields higher performance in this comparison. What I've found in these experiments is that tuning action horizon critically affects success rate. Mixing the VR and haptic data consistently yields better performance, and additional preprocessing is not always helpful. Thank you.
Yeah, so this is Yanbing Han from 45 Labs. So when we reach for an object, our eyes move first. This reveals human intent locking onto tasks, critical details before our hands ever begin to move. Our work captures this hand-eye coordination. We use Vision Pro for our capture device for its accurate hand and head pose. But since it doesn't provide eye tracking and raw camera access, we augment it with a RGB camera and an infrared camera, secured with a custom 3D printed design. With this setup, we built a data collection pipeline that synchronizes eye tracking, RGB image, hand trajectories, and head pose. So our dataset enabled robotic perception system to not just see the world, but anticipate it. Yeah, thank you.
And how can help with data curation? In last month, we started to see a big rise in open source data sets being shared in the public. These fantastic sources of data often might contain some episodes that might contaminate the training pipeline. We show how generative volume learning used as a helpful proxy for getting value or correlation. This allows us to spot episodes that could create issues during training. We have also run a comprehensive benchmark of multiple open source models, showing a big gap in performance compared to closed source. We share our benchmark and leaderboard where you can compare different models and datasets along with the code for reproducibility. Welcome new submissions, and we have hidden emails. Please see our OpenGBL space.
Collecting robot teleoperation data is too boring. Instead, we collect a large egocentric human task-oriented dataset. Here, task-oriented means the human data has clear start, end, and focus on specific tasks, just like robot data. We advocate human-centric representation, which represents actions using wrists and fingertip key points. It's an embodiment-agnostic representation that applies to any bimanual robot. We train a manipulation policy using the mixtures of humans and humanoid data. The policy predicts future actions as key points, which are then retargeted to robot actions. Empirically, co-training with human data improves the policy generalization across different background, spatial placement, and object appearance. It also enables few-shot policy transfer across different humanoid robots.
Hey everyone, welcome to our talk Grasp Factory, a large object-centric grasping dataset. My name is Srinivas. I'm a principal research scientist at Autodesk Research. In this work, we introduce a large-scale dataset of 6-TOF parallel jaw grasps for the Frank Panda and the Robotique 2-fingered 85mm grippers. We also train a diffusion-based grasp generative model on the Frank Panda subset and show that training on large geometrically diverse dataset leads to stronger generalization in simulation and real world. The current state-of-the-art dataset is the academic dataset that contains over 10.5 million successful grasps for the Frank Panda gripper across 8,872 objects. In comparison, our dataset contains 109.3 million grasps for the Frank Panda and the Robotique 2 and 85 grippers across 33,710 objects. We also train an energy-based diffusion model and show that training on large diverse dataset leads to generalization across novel objects.
We'll be presenting our work on understanding sim and real code training for diffusion policies. Simulation is a promising way to scale up data generation in robotics. Our work and others have shown that code training for both sim and real data can drastically improve. But what is the best way to leverage simulated data? And what are the principles underlying sim and real code training? We conduct a focused study guided by these two questions. In total, our experiments span over 300 policies, evaluated over 50,000 trials. More concretely, we studied the early scaling laws of sim and real code training, the effect of distribution shifts and the implications on policy training and simulator design, and the underlying mechanisms of code training, such as sim and real discernibility and power laws that predict real-world performance. I won't be at CoRL this year, but luckily my good friend, collaborator, and lab mate Nicholas should be at the workshop. Make sure to chat with him at our poster to learn.
Latent action models have quickly become integral to the pre-training pipelines of leading vision language action systems, as they promise to unlock vast amounts of unlabeled videos. At the same time, most latent action models to date have been trained on relatively clean datasets, such as in static scenes with a single manipulator. In contrast, real-world data often contains numerous action-correlated distractors, including background human movement. In this work, we propose to utilize the common-sense reasoning abilities of VLMs to provide promptable representations. We benchmarked more than 10 VLMs and conducted over 14,000 experiments to answer the following questions. 1. Whether VLMs are capable to produce promptable representations? 2. What is the best VLM that can provide these representations? 3. What is the proper way to extract these representations from VLMs? If you are interested in the results, see you at our poster.
Autonomous driving systems are usually trained on incident-free data that shows good behavior, but offers little guidance on what to avoid. Real crash reports contain that missing knowledge, yet they're difficult to use directly. We address this with a pipeline that takes a driving scene and candidate action and grounds the decision in retrieved precedents. We use both safe and unsafe data to enable the system to reason about a candidate action. At the core is a unified encoding that converts both multimodal driving logs and crash reports into structured graph representations, making two very different domains directly comparable for retrieval. On top of this, we design reasoning engines that decode a query scene using retrieved precedents. The counterfactual variant goes further by proposing alternatives, evaluating them against precedent, and refining its judgment before deciding. This doubles recall of reasonable actions. From 24 to 53%, models tend to be overly cautious, but our method makes them safer and more decisive. Counterfactual reasoning improves decision calibration. Thank you, and please reach out if you have questions.
Introducing RAC, Robo Learning for Long Horizon Tasks by Scaling, Recovery, and Correction. Conventional data collection mostly demonstrates successes, thus learned policy struggles when facing compounding errors. RAC is a lightweight mid-training phase after imitation pre-training. During on-policy rollouts, the human intervenes upon failure. RAC has two rules. First, recovers back to an in-distribution region, then corrects to finish the subtask. Second, terminate after the intervention. Training on RAC data composition teaches policies when to recover and how to adapt when going out of distribution. On short-hanging tasks, RAC achieves better performance than previous SOTA using 10x less training data. During rollouts, RAC policy consistently recovers from failures and reattempt to succeed eventually, demonstrating task time scaling. Success rate increases linearly with the number of recovery attempts and test time. For more details and videos, please visit our website.
The title of our paper is Beyond the Teacher, Leveraging Mixed Skill Demonstrations for Robust Imitation Learning. Imitation learning often struggles because the demonstrations we collect are noisy, inconsistent, and sometimes low quality. As demonstrated in the video, imitation learning methods fail to perform on this data. With too few expert demonstrations, the model can't fully capture what's important for the task, such as closure, symmetry, smoothness, shape preservation properties. To tackle these demerits, our approach begins by computing a demo utility score with multi-objective losses, allowing us to select the most informative demo. We then extract smooth canonical motion from the selected demo using periodic DMP. Finally, we refine the demos using an adaptive LSTM. This robust two-step pipeline enables data cleaning from noisy, non-expert demonstrations and produces reliable robot trajectories for real-world execution. As demonstrated in the video, our proposed approach tackles the demerits of noisy, non-expert demonstrations and generates clean, reliable robot executable trajectories for imitation learning methods.
In standard behavioral cloning, we map states to actions. But with limited data, this breaks down. Demonstrations vary in speed and often contain brief corruptions. Instead of learning from raw sequences, we reorganize data by what part of the task is being performed. We learn a progress variable from state alone, giving us a shared phase across demonstrations. This is discretized into bins. Within each bin, we compute robust summaries. The median state and median action act as stable anchors that represent common behavior. The magnitudes of these terms capture the typical strength of actions and the rate of state change, giving a sense of execution pace. Tangents of state and action describe the dominant direction of motion at that phase. To handle outliers, we estimate a trust score per sample, using leave one out comparisons, filtering inconsistent behavior. All this is combined into a ribbon token, a structured descriptor of phase-wise consensus and variability. We use these tokens to correct corrupted labels and train a simple policy with a weighted behavioral cloning loss.
It like disconnected and reconnected, so it's.
You should just put it down and then like yell into it. I don't know.
It's here.
Yeah.
Then, what? Share. No, this is live stream. Yeah, that's live.
You don't share.
Yes.
Yeah. All right. Connect to the Zoom and share your screen. You should. There, so be on the live stream.
Sorry, what's the link?
Oh, I sent you an email. I think I sent you the right email address. Yeah. There you go.
Share your screen.
I'm turning off audio. Grab a picture. Is the mic gonna be on?
Yeah, the mic is on right now.
Yes.
It's early.
Can I have 18 minutes?
Yes.
Okay, precisely.
We have
I will try to.
no worries. They said really appreciate it. This is great time. Which actually really appreciate.
I kind of like it. I just need to come on.
I assume during the time.
Not right. Okay, pass it to Philip. That'd be great. And also, like, the slides are not right, right there, they're really far. Awesome.
Hi, everyone. Welcome back to the Data and Robotics workshop. We're going to go ahead and get started with the afternoon talk session. Our first talk is going to be from Masha. Masha is a researcher lead and manager in the Large Behavior Model Division at Toyota Research Institute. At TRI, she co-leads the Trustworthy Learning Under Uncertainty effort in the context of robotic manipulation. Her research focuses on policy evaluation, failure detection and mitigation, and active learning. Previously, she finished her PhD at the Stanford Intelligent Systems Lab on uncertainty-aware perception for self-driving cars. Her work has been published in top-tier robotics conferences and machine learning conferences, including RSS, CoRL, ICRA, and NERV. So with that, let's have a warm welcome for Masha.
Thanks, everyone. How's everyone doing post-lunch? Still awake? Yes. Great. I love that enthusiasm. I'm going to talk about trustworthy learning under uncertainty for robot data, and conveniently, Joey already explained this slide. I totally tell you. We focus on evaluation, failure detection, and active learning / adaptation, and I will talk about some of these today. All right. So we've all seen really cool results from a bunch of different companies showing policies that can perform really dexterous tasks, long horizon tasks, can generalize to new manipulants, high precision, like the bike rotor task from TRI. This has all been really exciting. The success of all these models is highly dependent on data. So there's been a lot of open source and internal effort to scale this robot data, right? The video I have playing here is from Droid from a few years ago. And that's great. So great that TRI has recently put out an LBM 1.0 paper where we really set forth to rigorously evaluate whether this data scaling hypothesis is actually true. And spoiler alert, it is. So we found with statistical significance, on the left, we have simulation, and on the right, we have hardware. From these plots, we can see that scaling the data scales the performance. And the way that you can tell that it's statistically significant, these are called CLD plots. Basically, the alphabet tells you whether it is or it isn't statistically significant. So if you look at the left plot, you see A, B, B, C, D. Whenever you have a different letter, that means those two lines are statistically separable. And as you go up in this plot, you have more data. So you can clearly see the performance gains both on the left and on the right. That's great. One important type of data that's often overlooked is failure data, right? All these models, none of them are at 100%. And especially when we start seeing robots go in the wild, nothing's going to be at 100% success rate. So in the context of failure data, autonomously detecting these failures starts to become important. And why is that? Well, we could do a bunch of things with failure data. The most obvious one is safety monitoring, right? When we deploy something, we want to make sure that we have checks and balances for when things start to fail or have failed, and we need to figure out how to get back to nominal conditions. Failure detection also tells us about the limitations of the policy. The more positive view on failure detection is it can tell us what new data we need to improve the policy. It can also help us learn models of the environment or world models. It can tell us when to switch back to a different policy when we're in a weird state. And it can also tell us if we see failure rollouts, can we actually bring this back to the data and curate the data so that we have mostly successes. One point I'd like to make here that I feel pretty strongly about is regardless how much data we scale, we're always going to have a long tail. We're always going to have that one weird scenario where something fails, no matter what. And we need to be able to gracefully and safely react to these failures, which includes first detecting them. So one bullet point I'd like to zoom in a little bit more on is this data curation idea. In the last year, so this is all 2025, there's been a serious uptick in the number of data curation papers, which is fun and exciting, But why? So the reason why is it actually helps us adapt to environments. So let's say we start with all this data in all these different environments, and then we deploy in an environment that's slightly different than what we've seen before. So this is a slightly different blue color than on the left. What we can do is we can roll out a lot of the policies in our new environment and then take that information back to tell us about the data that we already have. And we can then rank this data as most useful towards contributing to success versus least useful. And then take that subset of most useful data for success and retrain our policy and hopefully improve our success rate. So this environment adaptation aspect to this is really exciting. So with that, these are the two areas I'm going to focus this talk on. First is policy-aware failure detection, and the second is deployment-aware data curation. Let's start with the failure detection bit. This is a paper that was presented by Chen Zhu 2 months ago at RSS, and he did an internship with us a summer ago. So he developed this method called fail detect, and it consists of 2 stages. Stage 1 is learn a score that's reflective of successes and failures. An important aspect of this, and this is really key, is the input to this score learning model is a feature extractor that is trained in the loop with your policy. So that's important because this tells us not just about the observations, but the observations relevant to your policy. And the reason this is important is we don't care if we're in an in-distribution environment or an out-of-distribution environment. We care whether the policy is going to fail, right? And that can happen in either case. So I'm showing an example of in-distribution setting where we have a normal towel that's been seen in the data and the policy fails. And then the alternate, which is new towel, never seen before, but ends up succeeding at the task. All right, and then the score itself is just a proxy for a negative log likelihood that we estimate through some flow matching techniques. Next step is we have all these scores. We have to calibrate a threshold, right? A decision point. And we do this using successful rollouts. We don't want to overfit to any failures that are particular to our data set. We prefer to model success for this work. And so everything, demonstrations, rollouts, everything is just using successes. And then the full system just looks like that right diagram there. We compute a score as we go through a rollout. And if that score is above the threshold, we flag failure. And if it's below the threshold, then we stay as success. Great. All right, let's look at some examples. So this is RoboMimic. This is the square task. What happens here, I'll play it again. We have a slip, failure detector reacts and says, hey, there's a failure there. This is transport, it's a handoff task. What's interesting about this failure, if I can zoom in on it, is the lid is thrown off. So the task has not actually yet failed, but the lid was out of frame and the failure detector reacts. And what happens afterwards is actually the policy messes up. So it fails to get the hammer because that visual observation messed up its policy. And then this last one is just a hanging task where it misses the hang and flags failure once again. Let's look at some hardware. This is a towel folding task. And we have an adversarial annoying human that's messing with the policy. So it is trying to fold, human gets in the way, and in this case, it messes it up. It misses this fold, and failure is detected. Similarly here, we have a challenging crumpled towel initial condition with a distractor, and in this bottom scenario, it again misses the fold, and the failure is detected. Let's give it a second. Here's the missed fold. There you go. I'll show a few more examples. So this is the coffee spill task that I showed at the beginning. The idea here is move the mug out of the way and then clean up the spill. And here we have a situation where it misses the mug. And so the failure is detected again. This one I actually really like, the failure case, because it misses the towel. and it starts to put the gripper into the coffee spill, which could be dangerous for the hardware, right? And the failure is detected before that happens. And shortly after, the human intervenes because we don't want to damage their hardware. So great, we have this two-stage score learning, threshold calibration, and then we have a failure detector. The awesome thing about this, to me, the takeaway, is that this policy-aware embedding is really useful towards this failure detection task. But in this paper, we only tested it in single task models. So in our collaboration with the University of Toronto, we actually extended some of these ideas, now using both successes and failures, to VLAs, so multitask policies. So can we have one failure detector for many different tasks? This is going to be presented at NERDS and has been an awesome collaboration with the University of Toronto. So let's talk about SAFE. The takeaway is surprisingly similar from fail detect. So I think this is probably my favorite figure out of the paper. What this is telling us, it's a t-SNE plot of the embedding space of a VLA. And on the left, we see successes and failures. Successes are in blue, failures are in red. The failures are all clustered together in this space. And that's really exciting because in that same cluster, we have many different tasks. That means that we have hope to generalize using this embedding space to detect failures in new tasks that we haven't seen before. So what does this look like in the embedding space? The success you can see is sort of populating in this blue space and staying out of this red region. And a failure starts out in a successful location in blue and then starts to fail once it messes up right here. And then it suddenly goes into the red immediately. So that's really cool. The system itself is very similar. Outside of now including failures to calibrate and to learn the score, again, we have these two stages. We have a score learning stage and we have a calibration stage. And once again, this looks very, very similar with now the change that the task has not been used for training the score or calibrating the threshold. And on the left, we have a success, and on the right, we have a failure that as soon as it goes outside of this threshold area, it's marked as failure. Basically, the robot's just stalling here. That's why it doesn't look like much is happening. Cool. So the takeaway is this policy-aware embedding space, super useful and informative for failure detection. And it will hopefully lead us to a place where we can actually reliably detect failures in tasks we've never seen before. And I find the definition of task can be fast and loose. For example, what if we have a new out of distribution object that we haven't picked and placed before, right? That might be a new task. So being able to generalize to all these differences is very exciting. With that, let's talk a little bit about deployment-aware data curation. This is a paper by Chris and Rohan, who are organizers of this workshop as well. And they're going to be presenting this paper tomorrow. So come by if you're interested. I have the information on the slide. And this has been an awesome collaboration with Marco and with Jeanette and Rika at Stanford. So the idea is we start with some data, some demonstrations, we train our policy, and we have our rollouts. And these rollouts come with success failure labels. So what we can do, like we talked before about this, we can send this information back to the data, and we can actually rate the examples in our demonstration data set so that they're most attuned to be successful in whatever our deployment environment is. So making this a little more visual, maybe we have mixed quality demonstrations that are not so great or are okay, and then we're seeing some mediocre performance in our policy. Can we make this better by manipulating the data? Here's the high-level idea. We start with our demonstrations, we have our policy, and this is the key right here. How do we predict this counterfactual question of how does the expected return change when we remove a data sample from our data set. And the larger this difference is, the more important that data sample is towards success in whatever deployment environment we're considering. I'm not going to go through all the math here, but give you a high-level intuition of how Chris computed this difference or this gradient. So the first is, this is essentially a policy gradient trick to achieve a tractable sum. And breaking up the parts of it, one, we have a Monte Carlo estimate, right? We take the expectation and we compute it through whatever number of rollouts we have with success failure labels. And the second bit comes from influence functions. And computing this tractably is actually from a work by Park et al. From 2023. So the basic idea is the higher this performance influence is, the better this demonstration is towards success. What I think is most exciting about this method is how effective it was. So I'll talk about 3 examples. The first is if we have mixed quality data regime, right? So if we have a mix of good quality data and maybe a robot teacher that's early in their training and the quality is not so good. If we just train this figure 8 task with all the demonstrations without thinking much about it, we get an empirical success rate of 36%, right? And you can watch it fail. Now, if we take away 2/3 of the data, we remove it, we retrain the policy, we get a success rate that's doubled. I get really excited about these numbers because I'm so used to seeing 5% differences, and this is doubled in performance. So that's awesome. Next scenario is this tuck box scenario. So we want to take a recycling bin and tuck it under a bench. The trick here is we have added weight to the deployment environment. So we have a weighted box in our recycling bin. And now we have a difference from our demonstrations. And in the demonstrations, we had 2 strategies. One was to push the box, and the second strategy was to pick it up and then just tuck it under. So we start by training all of it, and it chooses the wrong strategy because this strategy is probably easier for the network to just push it. 0% success rate goes to 84% success rate by removing half of the data. That's really exciting to me. And this last example that I'll talk about is the spurious correlation setting, where you have to pull out a book. And there are 2 strategies. One is if you have a stacked book, you want to pull this way so the book on top of it doesn't fall off. And if you have a single book, you can just pull towards you and nothing will happen. The problem with the data was you have a dark background whenever you had a stacked book and a light background when you have a single book. So during deployment, we had a stacked book with a light background, and the nominal policy had 44% success rate here. And you see the book on top of it fell. Now, again, taking away 2/3 of this data, it picks the right strategy. The book doesn't fall. Great. So the idea behind this work is that we're connecting policy evaluation, so the successes and failures that we observed in whatever deployment environment we have, back to the data set, and using that to adapt our data set to be maximally successful in the deployment environment. What was great about this is it requires as few as 10 rollouts and works, and it's performant across all these different data scenarios. So please come check out the work tomorrow when Chris speaks about it. In conclusion, we talked a lot about policy-aware failure detection, so that embedding space that's strained in the loop with the policy, and this deployment-aware data curation. So with that, I thank you, and I can take questions. Any questions? Yes.
Great talk.
Thank you.
Just to get a sense of precision recall on action, so kind of all of the
Yeah. It's a little hard. So I would say in balanced accuracy, we were getting something like 70% pretty reliably, both in hardware and in simulation. I would say that's probably where we're at, and there's definitely room to improve. But what I found exciting in the failure detection space was that it was consistent for simulation and for hardware. And we just kept getting the 70-75% accuracy, which was great. Problem is, depending on how you threshold, you can make those numbers go up and down. So it's kind of an iffy question. Yes.
Well, first point of the talk.
To
show this failure detection happens from the beach of the model. And it kind of means that model itself knows that it fails. Do you think it may work if we just like zero out this activation that's basically responsible for failure?
It's a good question. The question is basically if we zero out the activation that's responsible for failure. First, you have to figure out what activation exactly it is. The one assumption here is that the embedding space has to be not meaningless. So it takes a little bit of time for it to become meaningful and for the failure detector to work. So I would say that's probably a limitation. I think the question of how you figure out which activations are or are not useful towards the specific failure, and then if zeroing out would do anything useful or it would just break the policy, I think I'm not clear on. Thanks. That's probably fine, right? Thank you.
I think not that.
So our second speaker is Chelsea Finn. Chelsea is an assistant professor in computer science and electrical engineering department at Stanford University and a co-founder of Physical Intelligence. Her research interests lie in the capability of robots and other agents to develop broadly intelligent behavior through learning and interaction. Her research has been recognized by awards such as the Presidential Early Career Award for Scientists and Engineers, the Sloan Fellowship, and the ACM Doctoral Dissertation Award. Prior to joining Stanford, she received her bachelor's degree in electrical engineering and computer science at MIT and her PhD in computer science at UC Berkeley. Thank you, Chelsea.
Great, thank you for the introduction. So today I'd like to talk a little bit about what I think are some of the bottlenecks in developing robot foundation models. And to set the stage a little bit, at Physical Intelligence, we've been working quite a bit on trying to build more powerful foundation models, specifically vision language action models. And so far we've been trying to do that along a couple different axes. First, we focused on trying to develop really capable VLAs that can do really complicated tasks. And so in the first 6 months of the company, we were able to develop a model that could be post-trained to do a really complicated task like unload laundry and fold laundry. Certainly one of probably the most complex tasks that I've seen a robot do myself. And then of course, because it's a generalist model, you can also find it to do other cool things as well, like being able to put eggs into a carton and fold a cardboard box. And then from there, we kind of felt like one of the big bottlenecks was generalization to new environments, because these models were still quite brittle when you put them in different environments or when there's something changed about the existing environment. And kind of in the following 6 months, we were able to develop a model where we could kind of put it into a home and have it doing something fairly reasonable, even though it had never collected any data inside this particular home and a number of other homes that we used in our testing as well. So now kind of with this stage set, what are some of the bottlenecks for further progress in these generalist models for robotics? There's a lot of bottlenecks, and I won't cover all of the bottlenecks that I think are the most important, but in this talk, I'm going to talk about a couple major bottlenecks. And the first is speed, and the second is large-scale evaluation. So first, let's talk a little bit about speed. There's a lot of very practical use cases that demand suitably fast policies, and this could be for a number of reasons. So first, some tasks may be time sensitive due to the patience of a person that is receiving something on the other end, or economic constraints like the need to turn over kind of a plane that's being has maintenance on it, or turn over a hotel room or something like that. There's also scenarios where we want to be able to fit robots into human workflows, and if robots are a lot slower than humans, then it makes it a lot harder to fit them into those workflows. And then there's also just some tasks that are dynamic enough to physically require a higher degree of speed. Now, in terms of trying to address this bottleneck, one approach is to potentially speed up policies post hoc. And we've done some work on this. That was at ICRA last year. There's also, I believe, a CoRL paper this year on this as well, that tries to kind of take an existing policy and then speed it up after the fact. But really, the root of the problem is the data. A lot of the data that we train policies on is kind of slower than we would like it to be. So can we collect faster demonstrations? We've recently done a little bit of work on trying to study whether we can collect faster demonstrations. And a couple of years ago, we introduced the Aloha system, and it's arguably like a very performant teleoperation system. And it's like really exciting, the kind of number of tasks that you can do with Aloha, but it's still harder and slower than using your own human hands. So if you were to try to think about trying to collect demonstrations faster, there's a couple of things that you might consider as kind of the limitations. One of them you might think about immediately is that humans, we have like 5 fingers, whereas robots, we often use kind of parallel jaw grippers with robots, and maybe that is what's leading to slower speed. But in my experience, it's actually not the limiting factor for speed. And so with this in mind, I think that one of the kind of challenges with the Aloha is you do kind of have to be controlling a different robot system. And what if the operator could just hold the grippers themselves? Maybe that could allow us to collect faster demonstrations. This brings us back to what's known as kinesthetic teaching. I dug up a video of myself collecting a kinesthetic demo on the PR2 almost 10 years ago now. And obviously there's also a lot of work before 10 years ago as well that was using kinesthetic teaching. And it is promising, but also has some challenges. So robot arms can be large and heavy, like this PR2 robot arm. Human arms are visible during data collection and not present at test time, introducing a train test mismatch. And then lastly, you can only record the reach states rather than recording the actions that are actually commanded to reach those particular states. But we wanted to revisit kinesthetic teaching to see if it's something that might allow us to speed up policies. Specifically, what we decided to try is, instead of using a robot like the PR2, try smaller arms and try using gravity compensation to make it easier to move the robot quickly. To address the fact that human arms are visible, we can apply image masking or in-painting during both training and test time to reduce the train test mismatch. And then lastly, try to use a well-tuned high frequency, specifically 100 Hertz PD controller to be able to effectively match the kind of the reach positions that are recorded in the demonstrations. And then kind of the resulting interface looks something like this. So in some ways not too dissimilar from an Aloha-like setup where there are 2 arms. But in this case, the human operator is actually directly in front, even closer to the robot's own workspace, holds the grippers with some kind of handles on the grippers, and then can directly move the arms, potentially a lot faster than using an Aloha or puppeteering-like system. Now, how does this actually compare to using Aloha? We tested this with 1 expert operator who is on around the paper and 7 novice operators who didn't have much experience with teleoperation systems on a pretty challenging battery insertion task into a remote control. And in red, we're showing the kind of the learning curve of this novice operator on the Aloha system. And in blue, we show the learning curve over 10 trials on the what we call Aloha Lightning system. And what we see is that for novices, they're able to complete tasks 2 to 3 times faster when they're actually holding the grippers in their hands with gravity comp and so forth, compared to using a puppeteering-based setup. And then in these dashed lines at the bottom, we see an expert operator, and we see the expert operator on this kind of kinesthetic teaching system is near human speed at the task, where gray is just using human hands at this kind of battery insertion task. Now, even if we can collect demos quickly, that doesn't mean we can learn effective policies. And so we also use the masking approach to train policies and evaluate them on the robot. And we did this on a few different tasks. So here's kind of a 1x speed video of clearing a tray of objects into a bin, which the robot's able to complete in 7 seconds. Here's the battery insertion task that I mentioned before. The policy is able to complete it in about 6 seconds. Here the robot is kind of singulating a cup. So these are tasks that are really precise, and we really wanted to test the precision because we're not getting the commanded actions in the demonstrations, and this is stress testing the ability to learn from that kind of demonstration data. And then lastly, here's a shorts folding task where it's able to fold the shorts starting from a flattened position in 6 seconds. So all things that are quite fast by robot standards. Quantitatively, we also compared this to puppeteering with double the frequency at test time to try to post-hoc speed it up, as well as skipping actions. And we find that we get similar or better success rate with using this kinesthetic teaching teleoperation system. And the policies are 2 to 3 times faster than using puppeteering. So quite promising results. Cool, so that's on the kind of policy speed side. Now, another bottleneck that I mentioned is the scalability of evaluations. And the reason why this is a kind of a bottleneck is that even if you have a single task robot policy, this is already quite time consuming to evaluate because you need to sit down with a real robot and run the robot for multiple trials to get even just a single success rate number. And as our models become increasingly general and ability to do many tasks in many different environments, evaluation increasingly becomes a bottleneck. And one of the things that I found with generalist policies is that you'll evaluate them in one environment, and that the performance in that one environment will be completely different than the performance in a different held out environment. And likewise, if we start to see task generalization, we might see that it kind of generalizes really well to one task, but it really kind of generalizes quite poorly to another task. And this means that we need to collect data on lots of different environments and tasks, especially environments and tasks become individual test data points, and it becomes really, really hard to scale the evaluation of these generalist models. So how do we try to address this? I don't have the answer to this. It's really, really hard. But one thing that we've been exploring recently is trying to use generative models to evaluate generalist policies. And specifically, we're aiming to try to develop an action conditioned video generation model where we could potentially run the policy inside that video generation model to test the abilities of the policy. So to try to get this sort of action conditioned video generation model, unfortunately, a lot of the existing models out there, well, most of them are just passive models. They can't condition on actions, and so they aren't kind of immediately useful for evaluating policies. But second, a lot of the action condition ones aren't good enough, aren't accurate enough to really be used to evaluate generalist policies. So what we're going to do is we're going to use the pre-trained stable video diffusion model, and we're going to fine tune it on diverse robot data to try to learn kind of a simulator for this robot. The architecture looks something like this. There's a lot of details here, but I want to highlight a few different things. The first is that this video model is going to be using multi-view images. We're specifically going to be training this on the Droid dataset, and so it has 2 different base camera views and 1 wrist camera view. And we found that including all 3 of these views, especially the wrist camera, was really, really helpful for improving performance in a number of different ways. The second is that we're going to be conditioning on actions, and specifically we're going to be conditioning on actions in a way that's kind of aligned with the current frame prediction to try to make sure that the model is actually paying attention to the current action when predicting the current frame. And then the last thing here is that we're actually going to be using memory in this model as well. So we're going to be having past image frames as input to the model, as well as past proprioceptive input. And we're going to be using cross attention between the past frames and the past proprioceptive input to try to encourage the model a bit to be able to kind of use attention to recall past frames that have a similar arm state. And those frames might be the most useful for making the next prediction. And generally, this sort of memory overall will be really helpful for temporal consistency between future predictions and past frames. Cool. We trained the model on the Droid dataset using both the successful demos and the failed demos. And one thing that I'll highlight is that all of this model is pre-trained except for the action encoder. And this allows us to really benefit from kind of the web pre-training of this video diffusion model. Cool, so that's the model. Now, there's a couple of questions we can ask about this model. First, are the predictions any good? So here are some predictions. The top row is the ground truth. The second row is generations from this video model. And it's able to fairly accurately kind of move this bowl. Here's a video that's representative of prior work, and it actually kind of hallucinates a robot arm coming in from the right, which is kind of from the wrong side. And this kind of highlights the importance of having multi-view cameras, because it's actually, from the initial frame, it's really unclear where the robot gripper is. Here's another example where it's able to fairly accurately, but definitely not perfectly, model this kind of pushing this towel. And the prior work, in this case, is better at modeling the arm, but struggles to model the object motion. So the predictions look promising. There's a couple other important questions. The other is, does it react to different actions, passes input? Is it controllable and reacting to actions that are passed in? So we took an initial observation and we passed in different actions as input into the model. This is an action sequence that I think is just from the data. And so it's kind of predicting that it's going to pick up the marker. But let's look at some other ones. So here's a prediction of an action sequence that moves the arm in a different way. And one of the things that's cool here is you can see this making use of the other camera views, because this cup here wasn't in the initial frame. And it's able to see that there's a cup there from the base camera and then predict that in the wrist view. Here's another one where it's kind of rotating and also is able to make use of the different views to predict where the cup is in the wrist view. And then this last example is quite nice because we can see that it has good temporal consistency, where halfway through this video, the pen wasn't actually visible in the wrist camera view, but it's able to still accurately model the pen even after that. And so it's making use of the memory and the past image frames. So this controllability looks promising. And so from here, we started to try to use it for evaluation. And what we're going to be doing here is we're going to be taking the Pi 05 model and rolling it out both in the real world and inside the video generation model. And this is going to be for a novel robot setup with novel camera views, a novel environment, and so forth. And so, and basically both the Pi 05 model and the video generation model have to be able to generalize to this completely new setup with these new camera viewpoints, zero shot, in order to be successful. So it's pretty challenging. So here we see a prediction where the policy tries to pick up this blue block. We kind of immediately see a mistake here where kind of our model kind of doesn't get that it misses the first grasp and retries, but generally is able to capture a decent amount of what the policy is trying to do. It at least captures the intent. Here's another example that is kind of promising, but also has some issues in it, where the robot is trying to close the laptop. In real, it kind of makes it more on the second attempt, whereas the predictions showed it more closing it on the first attempt. And I should mention the world model doesn't get the languages input, only the policy gets the languages input. Here's actually one of the really good rollouts where the video generation model is predicting accurately that it's going to fold the towel. And here's another fairly promising example where the policy is going to be wiping from left to right. You can see that in the video, in the center view. And the model predicts that decently well with some mistakes at the end. So the model is far from perfect, but we note that it's able to evaluate the intention of, like, evaluate whether or not it's kind of the policy's kind of following the language command or trying to follow the language command at least. And so we're going to be primarily using it to try to evaluate and improve language following. So specifically, we quantitatively measured the correlation between the robot's performance in real and inside the video model. And we compared 3 different policies. We evaluated on a number of different tasks, both in real and inside the model. And first, we see that there's actually a really close correlation between these generated videos and the real world when you're measuring whether the model is attempting to follow the instruction correctly. Basically, whether it understands the instruction. And then second, when we actually evaluate downstream success rate, we see that the correlation is less reliable for this final success rate as shown here. And so it doesn't seem like these models are quite ready enough to be used as like a true kind of eval simulator for final success rate. Now we've been focusing a lot on evals, but as one final aside, we also try to use this world model to actually improve the policy on downstream tasks. And specifically to do this, we can collect rollouts. We can actually evaluate like our initial base policy inside the model on OOD instructions, label the ones that are kind of successful or less successful, and then fine tune the policy on just the successful rollouts for that downstream task. So specifically, we're going to be fine tuning the policy on generations from the video model, and no real data will be used to fine tune the policy. And then we can look at a few examples. So the first example is pick up the object on the top left side and place it in the box. These kinds of spatial relations weren't present in the base model's pre-training data, and so it picks up the incorrect object, it picks up the bottom left object. And then after fine-tuning on the synthetic data, the robot is able to correctly follow the instruction and more frequently complete the task successfully. You could also use pick up the larger red block. It doesn't understand things like larger, and so it picks up the smaller one. Whereas here, after fine-tuning on synthetic data, it follows the instruction correctly. And then lastly, fold the towel from left to right. Again, kind of left to right isn't in the base model's pre-training data, but we can then fine-tune it on synthetic data and is able to correctly complete the task. Quantitatively, we also see that on a variety of different OOD language instructions, the robot is able to have a higher success rate after fine-tuning on the data generated by the video model. Cool. So kind of in summary, I think we have promising tools for evaluating these two bottlenecks, specifically the speed of policies and the scalability of evaluations. There's also a number of important challenges that remain with these particular approaches. So with regard to kinesthetic teaching, we use masking of the human hands, and this seemed to work on the tasks that we were looking at, but they may block important task details for certain tasks. And it can also still be tiring even when you have gravity compensation turned on. And then along the front of using generative models, the model isn't quite accurately modeling the physical details, and we see this with a lot of generative models, not just our model. And so I think that thus far, what we've seen is that it can work well for instruction following, but can't work for generally improving the model in other ways. Cool. I like to highlight the students who led this work. Specifically, John led the work on kind of Aloha Lightning, and Yanjing led the work on using generative world models with Lucy. And if there's time, I'd be happy to take a question or two. Thanks.
Justin, we have time for one question.
Right.
So it's been tangential, but I'm curious, there's like all this video data on the world, and there's ways to leverage in the generative model of like kind of simulation. The other is that you can have video-based models, and then you find the policy like a base pre-trained model. If you have to choose one, let's say 5 years in the future, which one of these would make the biggest impact to the line?
If I had to choose between what and what, sorry?
Basically, like generative models that can create videos where maybe we can train them or something like that, versus video-based model where it could be used as like a binder domain like which would be the thing that would be made the biggest impact?
I think it's really hard to say. I mean, with the generative model, you can always generate a bunch of stuff and then train the checkpoint. So maybe that like encapsulates both in some ways, but maybe that's a cop-out answer. Yeah, I think it's really hard to say. I think thus far video generation models have not been accurate enough for a lot of robotics applications, even the really powerful ones. And so like pre-trained checkpoints seem to be really good. I think part of the challenge is we don't have that much robot data that's in these video models typically because there isn't that much robot data, or it's not like we don't have that, like we have some big promising data sets, but we don't have that much compared to all of the other video data. Yeah, I think a lot of work to be done.
All right, everyone, let's take Justin one more time.
So we get set up here where the mic is.
All right, everyone, as Max is setting up here, I'll quickly introduce him. We're very excited to have him here today. Simchowitz is an assistant professor of machine learning at CMU. His work studies the theoretical foundations and new methodologies for machine learning problems with an interactive, sequential, or dynamic component. He received his PhD from the University of California, Berkeley, under Ben Recht and Michael Jordan, and he completed his postdoctoral research under Russ Padrake in the Robot Locomotion Group at MIT. His work has been recognized with numerous Best Paper awards, too many to enumerate here today. And so without further ado, we'll let you get started with your talk.
Thank you. Thanks everyone for having me. Thank you, Rohan, for getting my last name right. That's incredibly impressive. Yeah, so this talk is going to maybe be a little bit different than other talks in the workshop and potentially other talks at the conference, in that it's going to bring a theoretical perspective on some of the things that we do in robot learning. So I'll just kind of get started. So I think kind of the theme of the workshop, and I think it's pretty difficult to disagree with this, is that modern robot learning is all about the data, right? So kind of 2, 3 years ago, 4 years ago, we started to see a bunch of different work. We try to make it easier to collect more high quality data across multiple tasks to enable kind of generalist policies. And certainly we've also seen these techniques becoming a really popular industry with recent startups, using these things to kind of have really impressive demonstrations. But at the same time, I think it's also rather uncontroversial to say that this kind of uptick in the success of robot policies kind of coincided with the discovery of a couple kind of quirky design methodologies that also seem to make things work a lot better, right? So like taking off with generative policy parameterizations like diffusion models and flow models, the use of non-learned control stacks, right? So we like to think we're doing end-to-end learning, but we pay a lot for our robots that have really carefully tuned hardware. And a bunch of other kind of essential, but still very somewhat mysterious design decisions. And in fact, today I'm just going to talk about one, but try to draw some broader lessons. So that design decision is action chunking. A little bit just kind of philosophically about why I'm talking about this. So kind of the claim that we're going to try to establish via action chunking is that modern robot learning and kind of many of the design decisions that we take in robot learning can really be thought about taking our control system between the robot and the environment and reparameterizing it in such a way that we can learn better. And it's kind of under the conditions of this reparameterization that we're now in a regime where things like the bitter lesson can take effect and where we can scale. And why bother understanding what works? I think this is a question that I personally wrestle with a lot. And I think as impressive as modern robot learning is, we still have major fundamental challenges ranging from dexterity to zero-shot dynamic transfer to reliability. And I really see this as just kind of at the beginning of kind of the road to generalist robots that can do all the little things we want them to do. And hopefully by understanding what works now, we'll have some more insights when we kind of face the more difficult challenges in the years to come. So just a refresher on what is action chunking. I think much of the audience might be familiar with this practice, but essentially what we do is we take some high dimensional observations that a robot sees, maybe a sequence of these observations. And then what we use these to do is to produce not a single action, but rather a chunk or sequence of actions, which we execute typically in open loop, or we execute some subset of these in open loop. And then finally, we deploy this, our robot sees the next states, sees the next sequences of observations, and we sort of go and we continue in this fashion. Okay. So there have been a number of hypotheses as to why action chunking may be beneficial. So for one, you might think that this improves representation learning, right? You're predicting an entire trajectory with kind of more meaningful information rather than just sort of individual actions at a time. You might think that using action chunking, it introduces non-Markovianity into your dynamics because you're sort of correlating your current actions with past actions. And this might be really useful if, for example, you have partial observability of the system. And lastly, there are lots of nice parallels between predicting long sequences of actions and proceeding horizon control, right? So making a longer term plan and only enacting a little bit of it. But in fact, what we're going to show later in this talk is that there's an experimental setup which ablates these things away and shows that even though certainly these could be benefits, even in regimes where none of these hold, we still see benefits to action chunking, right? So even the benefits of action chunking persist even when we don't really persist if we only predict one action. So it can't simply be about representation learning about the prediction objective. The benefits persist in state-based control with full observability. So it can't purely be about resolving non-Markovianity. And finally, if you execute an entire action chunk, you can still see tremendous benefits. So it can't still be just about proceeding horizon. So we'll try to dig into what's going on. So the complementary perspective that I'm going to bring is action chunking is actually should be understood as a control theoretic tool. Benefits are control theoretic in nature. And they're witnessed even in the simple setting of state-based deterministic policies, which is not the setting in which action chunking was first proposed. So let me kind of just describe where I'm coming from. So we can think of robot learning as a control problem. This should be relatively uncontroversial, right? So we take actions, the actions proceed through our dynamics. The dynamics affect state, which typically we don't get to fully see. We only see some observation, but we plug that observation back into our policy, taking new actions and so on and so forth. So that's not so interesting. But I mean, maybe what distinguishes control from a general MDP, from general decision-making like you might see in RL, is the presence of decision-making in the presence of stability, right? So as control theorists, kind of the central object that they consider is this notion of stability, which roughly refers to the sensitivity of your dynamical system to perturbations of its inputs, right? So kind of the two canonical cases you can think of stability, I'm not going to give mathematical definitions because it's a short talk, but a system is stable, think about a regular pendulum, right? It's upside down, and so when you perturb it, it's going to sort of relax into its equilibrium. On the other hand, if we have a pendulum on its other side, right, any small perturbation can knock it over. It's highly sensitive to these perturbations. So there are a number of scenarios of what we call incremental stability, which focuses on the sensitivity of inputs. So where we can think about some malicious adversary that's going in and perturbing inputs to our system. We'll say a system is open loop stable if just perturbing the inputs doesn't cause the system to change too much. This is typically the case that we see in modern robot learning with the kind of pushing, pick and place tasks, kind of pushing objects. Systems are relatively stable. There's also closed loop stability. So this is what happens when we have a policy running in feedback with our environment, and it says that perturbations of that policy also won't cause things to go too far awry. But the last scenario that will also arise in this talk is the notion of closed loop instability, where if we make perturbations to our policy, this is going to cause feedback with our system that will push things further and further off course as time continues, right? And this is the situation that we want to avoid. And I should also mention that there is open loop instability, but in modern robot learning, this is something that we're not really tackling quite just yet, at least in manipulation. So why does stability matter in robot learning? Well, we can think about behavior cloning, right? So imitating an expert demonstration. So imagine this is a trajectory of an expert in cartoon form, and we'll assume that the expert is always closed loop stable, meaning your teleoperator knows if you make a little mistake how to get back on course. So what are we doing in behavior cloning? What we're really doing is just learning from the states in the expert distribution. So we're trying to make predictions of actions that, when anchored at the states in our data, are close to what the expert would do, right? But of course, that's not what actually happens when we deploy our policy. When we deploy it, we take actions in sequence, and these errors that they make can compound over time, leading to further drift away from the distribution that you want to imitate, right? So we call this the compounding error problem. You can readily see that if your learned policy is closed loop unstable, you're not going to be in for a good time, because small errors that you make are going to be transferred and are going to kind of grow considerably larger. So what can we say theoretically about this? We can actually create the following mathematical construction. So fix any target error scaling law that you would like, say polynomial inverse of n. And what we can show is that there exists open loop stable imitation learning problems, where actually both the dynamics are stable and your expert demonstrator are closed loop stable. But you run into the following issue. Your validation loss in your behavior cloning problem obeys your scaling law, goes down like n to the minus alpha. But if you try to deploy your learned policy, this is going to blow up by a factor of 2 to the horizon. So it's going to be exponentially worse, right? And this is somewhat surprising, because this is happening even if our dynamics are nice, and also even if our expert demonstrator is also really well behaved. And really, this is an issue that doesn't depend on behavior cloning. It actually happens for any imitation learning algorithm. It's much more tied to the policy parameterization. So this is policies that are not doing action chunking, rather than the algorithm. So if you did inverse reinforcement learning, if you did Q learning, you're not going to break this negative result. So why does this happen? Essentially, what we show is that there exists a setting where no single policy is both consistent with the expert data, but can stabilize all possible dynamics outside of the distribution of the expert data. So imagine that your expert data manifold is kind of lying on the y-axis, it's in the blue. And you can imagine trying to design a policy that agrees with the expert, but when you go off course, it would still stabilize the dynamics if the dynamics were given by this gray function, F1. But it turns out, unfortunately, that there will be some other dynamical system, which you don't know, you haven't seen data there. And if that were the true dynamics, you would unfortunately have to destabilize it. So you really cause this kind of catch-22 where you're not able to stabilize one or the other. And you can check out the paper to see what the mathematical construction looks like. So a couple issues or notes. One, if you had good non-expert data, that would fix this, right? This is the data curation workshop. So I think this really also says that there are other ways to do things in terms of great data curation. But of course, we can never collect all the possible failure mistakes in the world. We did at least like policies that have some inbuilt robustness. I think the second note is that this is very different from other settings where we use pure supervised learning for pre-training. So for example, in discrete settings like LLMs, compounding error is only at linear in the horizon rather than being exponentially large, right? So this is something that's very unique about learning in the continuous physical world. Cool. Maybe one last other point of contrast. So in traditional control, for example, in the 70s, when people were trying to fly airplanes in like the Cold War, the real challenge was that your dynamical system itself was really nasty. You had to stabilize an airplane that had to be incredibly agile to do these crazy maneuvers. In modern robot learning, at least for the task we're thinking about, the dynamics are actually quite nice. What's really hard is that the black box policy itself is the thing that has to be stabilized, both because the neural network might be ill-behaved, but also because it has to be queried in OOD situations. And so I think reframing state stability from something that's about hard dynamics to difficult learning conditions, I think is something that's going to be quite novel that we have to encounter in modern robot learning. Okay, so where does action chunking come in? Remember, in action chunking, what we're doing is we're predicting sequences of actions rather than actions in open loop. So actually, we're able to show something that's quite remarkable, that if you just do action chunking with a fixed but sufficiently long length, you break this exponential compounding error issue. So rather than having 2 to the h multiply your scaling law is multiplied by a fixed constant. Essentially, action chunking is avoiding compounding error. And really what this bound does is it saturates at a fixed chunking size, right? So it doesn't say that you're, it's not like just saying, oh, I'm just shortening my horizon by some effective amount. It's really saying that I'm changing the fundamental dynamics of my control system. And we can actually simulate this on I'll get to more interesting experiments later, but we can simulate this on our toy construction that witnesses this mathematical counterexample. And you can show that as you use smaller and smaller action chunks, your compounding error is less and less drastic, or larger action chunks, your compounding error is less drastic. So why does this happen? Really what's going on is that the rare policy updates are leveraging the open loop stability of the dynamics. So even though you could go compound and go way out of distribution, sort of if you use the fact that the dynamics are stable and aren't too sensitive to perturbations, you kind of allow the dynamics to carry you back to where you would have gone otherwise. And we can make this precise in mathematical sense, but it's a little hard to do for a short talk. So maybe one way to think about this, way I think about this, is action chunking is actually creating a different dynamical system. So now your dynamical system doesn't take in one action, but it takes in a sequence of actions. And it turns out that in this parameterization, the imitation learning problem enforces closed loop stability of the learn policy, allowing you to avoid exponential compounding error. So how do we test this hypothesis? What we do is we set up a situation where we can ablate away the other possible explanations for action chunking. So we look at a state-based regression policy trained from a deterministic expert. What we do is you train a flow policy and you generate data by flowing it from zero and do some filtering to make sure you have good demonstrations. And so what we can show from here is that there are certainly gaps. So in the different colors, what we're predicting are the different action chunks that are done in training. And on this axis, we're looking at the evaluation rate. And certainly it's the case that the amount of actions that you predict does affect the performance, but you can see that the dominant trend is really the length of the actions that you execute, right? Rather than the actions that you train on, which give credence to this hypothesis that really it's about executing long actions, chunks, and reparameterizing the dynamics that drives the effective action chunking. So this is also very consistent with why we find that we use end effector control parameterizations in robot learning, right? Remember, our core assumption for why action chunking works is that the dynamics are stable. And it turns out that end effector of control precisely puts us into this regime, right? So when you make position commands, what it's essentially doing is it's just tracking the positions that you desire. And so if you made a little mistake, well, your position control can make up a large amount of the difference, right? So this kind of, what this really suggests is that sort of action chunking and end effector control have this unique synergy, which is avoiding this exponential compounding error and really making our scaling laws behave a lot more nicely. Cool. So again, of course, theory doesn't tell you everything. There are lots of banal hypotheses for why action chunking work that are also valid. So for example, when we collect expert demonstration data, oftentimes it has a lot of pauses. If we don't do any action chunking, we can just get stuck in an infinite loop. So I think it's important to keep in mind, this is not sort of a totalizing explanation, but I think the controlled theoretic explanation still does help. And I think the previous experiments we showed sort of provide evidence as to this effect. So what happens with unstable dynamics? I'll mention this very briefly. It turns out that with unstable dynamics, right? So imagine like, you want a robot basketball player or something crazy. You're not going to really, your imitation learning alone is really not going to be able to cut it, right? So what we can show is that in this case, there's no algorithm, right? Without collecting more non-expert data that's able to beat this 2 to the h compounding error, right? So our scaling law is kind of putting us into this valuation. And really what this says is that when we're doing unstable robotics, as we move towards more dexterous, more difficult tasks, we're going to need to increase the coverage towards non-expert demonstrations as a form of learning, or alternatively use interaction reinforcement learning as a way to train these agents. So maybe just let me recap and then kind of go from here. So my kind of claim that we try to show in this talk is that modern robot learning, the design decisions that seem mysterious are really about reparameterizing the closed loop dynamics between the robotic agent and the learner more broadly. And that essentially what's going on is it's not that the dynamics are super hard, but rather that our policy, this stabilizing this learned black box policy OOD is the fundamental challenge that we have to circumvent. So maybe what I'm going to ask is, can this perspective be more useful beyond just action chunking and give us insights into some other design decisions, right? So actually in some soon to be released work, we're actually going to try to answer the question, why do we use flow and diffusion policies? And I can't go into it here, but the big TLDR is that generative controllers are really about regularizing OOD behavior. If their fundamental effect is this, in fact, multimodality is quite limited. It doesn't show up in almost any of the popular robot learning benchmarks. It's really about regularizing OOD behavior. And then in some work I'm incredibly excited about, but unfortunately can't share too much about, it's still in progress. We're able to show that changing the optimizer itself for how you train, so it's changing from Atom to some other kind of optimizer, is able to prevent sort of distribution shift within the layers of the network itself, improving imitation learning performance tremendously, right? So again, you see the theme is that sort of all these design decisions really come to regulating OOD behavior, encouraging various forms of stability and reducing compounding error. And of course, in addition to all these, still there remains the kind of the big question, how we use these insights for the data. I won't have much to say about them today, but probably the most important part of all the robot learning research we do is the students. So I want to thank Thomas Zhang and Daniel Frommer for leading this work, and their advisors, Nick Montney and Ali at MIT. Thank you.
You can take a couple questions.
Yes.
So these results change the action space is the same, for example, as in velocity space.
Currently not. I would imagine that you can reparameterize them so if they work in velocity space, it would work as well. Right. Yes.
We cover utilization variables today. Mention chunking general is what have you had a chance to look?
So I've in my experience at least in many computing applications, it works best when you do action lumping. At least 24 steps. I mean, I've seen in many cases action lumping products. So, yeah, in fact, so these done this a lot of them. We get more action.
So in order to successfully to RL, they had to still have yes.
No, I think the question is if you're doing that for on-policy or else it's not. The on-policy reinforcement, at least my medicine's group. So I think at least in on-policy reinforcement learning, no additional modifications have to be made. If you want to use off-policy reinforcement learning, you need a key function. And when you have a key function, you have to attend to longer sequences of action. So typically this requires some architectural design decisions to be made, but it's really about the policy representation. It's not really the action. Actually, what I would say is probably in RL, you need action chunking less, or ideally you should need it less because you can overcome the instability through online interaction. Yeah. Yeah.
All right,
Cool.
everyone, let's take that one more time.
Yes.
And if that was very good break, we'll be back at 2 p.m. for tutorial on data mixing and then 3:40 for the panel session.
We do, yeah. Okay. I think I had it back. No, but it'd be great to have it, but it's okay. Let me see. Let me see. About 50 minutes. Yeah, that's basically. But yeah, no worries. No worries. Yeah, no, I bet. Okay. Yeah. Okay. But I work with it in our lots of attendance, which then Max. Yeah, Max does great work. I mean, that's not easy stuff. I mean, that's a quite good piece, and then actually, but it was very good. Yeah. Okay, we'll see you. Yeah, we'll get dinner or something. See you.
Yes.
Okay, everyone, we're gonna get started. We're gonna have a tutorial on data mixing. So Mayee Chen is a PhD candidate in computer science at Stanford University. She's advised by Professor Christopher Ray. Her research focuses on advancing the fundamentals of artificial intelligence through data-centric approaches, particularly in training data curation, where she has developed techniques for data mixing, curriculum learning, and weak supervision. Her work has been recognized with the Best Student Paper Award runner-up at UAI 2022, a Best Paper Award at AAAI 2022, and spotlights at iClear and Europe's 2023. Mayee is currently a research intern at AI2, driving the data mixing efforts for OMO3, their next generation open source large language models. Before Mayee gets started, I just want to say it's super exciting that she's here with us, because it's often very difficult to get a non-roboticist to show up at workshops, and we think there are a lot of interesting insights in large-scale training of language models that apply to large-scale training of robotics models these days. With that, Mayee.
Thank you, Chris, for the lovely introduction. It's great to be here. So my name is Mayee, and I'll be presenting a tutorial on data mixing, which is a powerful tool in curating training data sets. So in the LLM world, it is increasingly accepted that good data is critical to the performance of models. So the latest models are trained on over 30 trillion tokens, and every organization that is training an LLM basically has an entire team working on making sure that the data is as good as it can be. Recent model reports like for Llama 3 also repeatedly highlight the investment made into constructing data sets. So I thought it might be helpful to first look back at how we got here. So how did the field of AI get to this point of recognizing the role of data? So you can think of two core parts of an AI system, the training data and the model. And so for many years, people had focused on model-centric AI. You use a well-known training data set like ImageNet or CFAR, and you would focus on improving the model architecture and training procedure. Then starting in around the late 2010s and early 2020s, people started thinking a lot about data-centric AI, and they realized that a lot of performance gains were in the data. So you could just use a fairly standard model architecture and training procedure and really just focus on improving that data. And here was when people started thinking about things like automated data cleaning, data augmentations, and a lot of techniques. So while this data-centric AI idea was growing largely in enterprise AI, the LLM story was a little bit different. So around the same time, the first modern language models started coming online, and each of them had more and more parameters, as shown in the figure on the left here. And scaling laws research really suggested that all you needed for better performance was more parameters and more data. So as time went on, people started training on larger and predictably messier data sources. So for instance, BERT, which was from 2018, was trained on books and Wikipedia, while GPT-2 was trained on Reddit, and GPT-3 was trained on a mix that included Common Crawl, which is massive open web scrape containing over billions of web pages of data with highly variable quality. So of course, during this time, there was definitely still a hunch that quality and other properties of data still played a role, but a lot of the previous data-centric work was at a smaller scale, and there weren't many studies that demonstrated if better data could shift how to design these large language models. In around 2022, however, we started seeing these first large-scale studies that showed that quantity was not everything. So several papers started showing that smaller, smartly pruned data sets could actually be quite advantageous, as suggested in the plots here. So from here on out, people started more widely accepting the fact that having good LLM training data was important as having a lot of data. So lastly, before I go into more technical components of the tutorial, I wanted to share a bit about my background. So I'm not a roboticist, but I'm always curious about the area. I work a lot on LLM data, and I partnered with various organizations such as Snorkel AI, Together AI, and the Allen Institute for AI. And I've been involved in the creation of several language models and their large-scale training data sets. So I really hope that this tutorial can encourage our two fields to have more conversation around developing data-centric approaches. So the rest of the tutorial is shown here. First, I will discuss the general LLM data development pipeline, breaking it down into what are properties of good data and what are the mechanisms for creating a good data set. Then I'll go into my area, which is data mixing. Broadly speaking, data mixing is a mechanism for combining data sets. So I'll go over the basics of why we need this and what it is. And the technical meat of this part would be on something called mixing laws, what I believe is a fundamental unlock that really elucidates and organizes this research space. Then I'll discuss several methods that are built on mixing laws and the implications of these mixing laws. So there are many things that can define good data for LLMs, but here I've broadly categorized them into 3 buckets. Quantity, which is just the number of tokens, quality, which you can think of as sample level properties, and composition, which are dataset level or group level properties. So first, even though I said earlier that quantity isn't everything, it's still incredibly important. So you can see that with the growing trend that even the latest LLMs continue to be trained on more and more data. So for instance, you can see for the Llama family, it's been consistently increasing up to 30 trillion tokens. Second is quality. So you can think of these as individual characteristics in these text samples. So for instance, here I'm showing you some samples from a data set called FineWeb EDU. For the EDU part, basically what people did was the Hugging Face people trained a model to score how educational each sample was, and they only kept the samples that had a score of higher than 3 out of 5. So in the red and the blue here, you can see that you want to keep these samples that are high quality, like the definition of a vaccine here, and you want to remove these low quality samples, like the one, the red one above, like it doesn't really say much. And then finally, we should care about the composition of the training data set. So when training a model, you usually want it to do many things well. You may want it to summarize long documents, write code, talk with us, do all these things. And so naturally, the training data should be composed of data sets that consist of these long documents, this code, this dialogue, and all these things. So we need this notion of kind of like matching between data sets and the desired capabilities. So we've discussed these 3 nice properties that we want, and now how do we go about achieving those? Here I've abstracted data development into 3 mechanisms: acquiring data, which increases quantity, transforming data, which improves quality, and mixing data, which helps control the data set composition. These 3 mechanisms are typically chained together in the following way to get a final data set. So first, you would acquire various sources of data. For example, one practitioner is responsible for curating the GitHub data, while the other one curates the Wikipedia data. And then each of these data pools are transformed, and finally, they are combined via mixing to produce the final training data set. So next, I'll provide an overview of each of these mechanisms and the techniques that are being used there. All right, so first is data acquisition. You can think of this as really just going from no data to some data. And nowadays, there's so many ways to do this for LLMs. You can crawl for the data yourself, or if you want something simpler, you can download an existing data set. You can also synthetically generate the data, which is pretty cool. This was an idea that kind of grew from the Microsoft Phi models, and one of their papers called Textbooks Are All You Need. And more recently, this has been done by the Hugging Face team with this data set called Cosmopedia. And basically what this does is you have some seed samples that are true data, and you get an LLM to create new samples based on those. All right, next is data transformation, which can be categorized into data filtering and data rewriting. So first, data filtering is a massive area, and I could talk about this for a lot more. But there's a ton of things you want to filter for, basically. And they kind of go from coarse to fine. So at the coarsest level, people will filter for things like punctuation, certain keywords, URLs. These are just like heuristics that the practitioner knows, like this URL doesn't have anything of value, it's just not included. Then going a step farther, it's also important to deduplicate. So the idea here is that you don't want a sample that appears over 1,000 times in your data set, but when you're scraping the web, a lot of content is repeated on different pages. Finally, moving towards the more advanced types of filtering, you can use a model to determine if you want to keep or discard a sample. So for instance, what I mentioned with the Fine Web EDU samples earlier. And also you can filter not only for quality, but you should also filter for things like safety, sensitive information, licensing, and so on. The second category we have here is rewriting, which I would say is a somewhat newer type of data transformation that a lot of people are starting to look into. So the main idea here is to transform a text document into a particular format. For instance, you take some web page and you create question answer style writing, or you rewrite it as like a Wikipedia style page. And that kind of improves the quality and aligns the data more with how people use these models. And then the last mechanism is mixing. So this one focuses on taking M data domains and combining them to create a final data set that leads to a range of good model capabilities. And this, of course, brings us to the next part of this tutorial. So now we're going to go over a more detailed look at data mixing. So as I mentioned before, mixing is the procedure of figuring out what ratio you need to combine your data sets, such as your model exhibits all these capabilities. More formally, we have a set of M data domains, and we want to determine in what ratios, P, should we sample the domains to produce a strong model. Before we start discussing how to mix, it's actually important to also step back and ask, why do we even need to mix? What does it enable? And the reality is that modern LLMs are not trained on a single data set. They're almost always trained on a collection of different sources, simply because there are so many places to acquire data from, and there are many people curating these data sets at the same time. So in some sense, mixing is inevitable. And even if you said that you didn't want to do mixing and you just concatenated all your data sets together, you effectively are still inducing a mix, like a ratio over your data sets. So it's natural that we want to get the most performance out of a procedure that is inevitable in the data development pipeline. Then beyond being kind of inevitable in practice, mixing is uniquely useful in that it allows us to control the training distribution using the mixing ratios as a low dimensional knob. So adjusting this knob helps us smartly navigate and optimize trade-off space among various model capabilities. And we indeed do see that mixing, when done well, can improve performance dramatically across model capabilities. So in the figure shown here, the green line indicates a good mix from one of my papers, and you can see that on all 9 tasks, it obtains better performance than the other 2 mixes. So this shows that mixing can really make a difference, and therefore it needs to be done with thought. So a very straightforward way of getting a good mix is to simply apply a naive search-based method. This would mean that you start with some mix, you train a model using it, you see how it is, and then you continue to manually adjust the weights based on these vibes, as they say. And the problem with this search approach is that it's quite costly, and it requires you to train a bunch of models on different candidate mixes. However, I will say it is a tried and true technique. It's been used across different models and domains over the years. So next, I'll go over the 2 settings for mixing and their formal problem setups. In data mixing, we consider what are called static and dynamic settings. So in the static setting, we determine a mix P, and we train the model, the entire model on it. So we just fix P, and we train for, then we just hit run. In the dynamic setting, we adjust the mix throughout training such that the model is trained on the initial mix for some number of steps, then another mix for some more steps, and so on. And currently, I'd say that there's not really a right answer for whether static or dynamic mixing is better to do. It really boils down to what are the pros and cons for the practitioner. So for static mixing, the main advantages are that it's quite simple and reusable. So you prepare your training data set according to the mix, and you can hit run and you can do everything else normally. These mixes can also be reused and passed down as good references for future models. So if I see a paper that reports, you should have 30% code, then I know that, for my next model, I should use a similar math. The one drawback, however, for static mixing is that it could be possible that it doesn't fully take advantage of how the model changes as it's trained. So there's a risk that a static mix becomes stale as the model continues to train, and then it'll be suboptimal. So this is where dynamic mixing shines. It allows you to adapt your mix as the model learns. And this can be quite beneficial in some cases. So for instance, in some of my previous work, I showed that it's helpful for the model to learn 1-digit addition before 2-digit addition. And so a dynamic mix could take advantage of cases like this, where you start with learning more of 1-digit addition, and then as that skill becomes mastered, you would adjust your mix to learn 2-digit addition. The problem is that there are a few drawbacks of dynamic mixing, which is that it's not very straightforward to implement. It's not compatible with a lot of standard trainers. And the dynamic mixes are specific to the model, which makes it difficult to reuse and pass down as bulk knowledge. So we've established that both of these settings are valid and worth studying. So now I'll give the formal problem definition for the static mixing problem. So we're given M training domains D1 through DM, and we want to train an LLM on N tokens. The data mix P is a probability vector over the M domains, and the final mixed training data set is created by sampling N times P of I tokens for each domain DI. We then denote LM of P as a model trained according to data mix P on the domains, and then we evaluate this trained model on N validation data sets, where F of I of LMP denotes the validation loss on data set I. So for these validation data sets, you can think of them as either held out splits of the training domains, which means that N equals M, and we're just evaluating in-domain performance, or these validation tasks can also be out of domain, such as downstream tasks. Now, the static data mixing problem is to find the data mix P that minimizes the average validation loss over all of these validation data sets. And the main goal is if we can compute this optimal P in a way that is more efficient than just a brute force search. Next, for the dynamic mixing setting, we split training into T stages. And so rather than having the mix P be held constant throughout training, we consider a mix that can change at every stage. So we train on data sampled according to P1 for the first N over T steps. We train according to P2 for the next N over T steps, and so on. This makes the dynamic data mixing problem much harder. We want to learn the optimal mixture trajectory, the sequence of P1 through PT, and we want to compute this trajectory efficiently. So as you can imagine, these are pretty hard problems because the search space over mixes can just be very large. And over the past 2 years, there have been a lot of data mixing methods proposed, and they're doing all sorts of things, including some of my earlier work, like some are using bandits, some are using portfolio optimization, and every single one of them works quite well on the data sets they evaluate on, but it isn't really clear which one is best and what they're really doing under the hood. And so sometime around last year, amid all these methods, several papers, including one of mine, started to chip away at this fundamental development called mixing laws. The key insight here is sort of a scientific one. which is that there is a structured relationship between the data mix P and the performance of a model trained on P. And the significance and why this was so exciting to me is that if there's a structured relationship between the mix and the performance, we should really be thinking about how to understand this relationship and use this relationship to guide our data mixing. And this was a fundamental shift for me in how to really view this space. And it moves the question away from, let's just design a method that obtains a good mix, to this question of understanding and exploiting this scientific property of how models learn from data. So this particular structured relationship is shown here. The relationship between the mix and the performance of a model trained according to this mix follows quite a simple parametric form. And the key property to note here is that F, the performance, is expressed using a linear function A transpose P, on top of which other monotonic transformations are applied. And so this structure and this linearity is quite interesting. So what this means is first that small changes in P result in small changes in model performance, which makes sense naturally. And second, this linearity is super interesting. It means that each domain additively contributes a term Aij to the performance. And so this Aij can be thought of as a true score for how much domain J impacts validation data set I. So I've shown the general format of this structured relationship expressed as this roughly linear mixing law. And so now I'm going to go into two methods, one static and one dynamic, that focus on first understanding this mixing law and then utilizing it in their algorithm. So first is a paper called Data Mixing Laws, which I believe was the first to coin this term and come up with this structure. And this paper focused on the static mixing setting. In particular, they showed that the validation loss could be approximated as an exponential and linear function on the data mix. And in both their experiments and my work, it's been pretty rigorously validated that this mixing law holds quite well in practice. So in the figure here, you can, what we're doing is we're mixing over just two domains, archive and stack exchange. And on the x-axis here, we're changing the proportion of the domains, and on the y, we're observing the validation loss. And you can see that the performance predicted using the mixing law very closely aligns with the true performance. In addition, the R-squared value of the static mixing law on Slim Pajama, which is a popular pre-training data set, is quite high. So once this paper established the validity of this static mixing law, they focused on how to use this. So their approach could be broken down into three stages, what I call explore, fit, and optimize. So explore and fit involve learning the mixing law, and optimize involves exploiting it. So first, in the exploration stage, many small language models are trained on a bunch of different mixes, and we record the validation losses corresponding to each mix. This creates a set of inputs P and outputs Y, and in this fitting stage, we use this set to estimate the parameters of the mixing law. Once this mixing law is fit, this essentially gives us a surrogate model that can predict the performance of any mix we pass into it. And so in the third stage, optimization, we use the mixing law as a substitute for the true relationship F, and we can efficiently solve this optimization problem using standard solvers. This method introduced in data mixing laws was shown to improve performance. So as you can see in the figure here from their paper, the mix they computed was able to be 1.48 times more data efficient than just random sampling of the data. Next, I'll discuss one of my works called Aioli, which discovers a dynamic mixing law and utilizes it in a mixing algorithm. In particular, we constructed a time-dependent mixing law where the validation loss at stage t+1 is equal to the validation loss at stage t minus some linear function of the data mix at stage t. So intuitively, this shows that the marginal performance improvement at each stage is linear in just the current data mix. So in the figure here, you can see that this dynamic mixing law also fits the true performance quite well, and the R squared on SimPajama is quite high. So now that we've established the validity of the dynamic mixing law, we want to figure out how to exploit it to create a better mix. The simple solution proposed in Aioli was to split each stage into an exploration and an exploitation phase, as shown by the blue lines and the orange lines. So in the exploration phase, a procedure very similar to the static case is done, but sequentially. So we sequentially train our model on a bunch of different mixes and record the change in validation loss each time. And this creates a set of inputs P and outputs Y, and we can use this set to learn the parameters of the dynamic mixing law. Finally, in the optimization stage, we use this dynamic mixing law as a surrogate model in place of the true F, and we update our data mix accordingly. So we'll use this data mix that we computed for the remainder of this stage. And once we move to the next stage, we will repeat this entire procedure of exploring, fit, and optimize. Our method Aioli demonstrated clear performance improvements. So as shown in this figure, we compared Aioli's dynamic mixing approach with data mixing law's static mix. So we considered 5 different data domain settings. And across all these settings, Aioli consistently offered improvements. And so the key takeaway here is that there is value in dynamic mixing over static mixing. Now I'll move on to why I am very excited by this way of thinking about data in terms of these mixing laws. So in particular, these mixing laws are an incredibly useful tool in understanding both existing mixing methods and understanding our data more. So as you may have noticed in describing the static mixing laws in Aioli, both of them followed this procedure of explore, fit, and optimize. And it turns out that many mixing methods also follow this approach. However, the key difference is that a lot of existing methods do not explicitly fit a mixing law, yet these approaches do make some implicit assumptions on the relationship between the mix and performance. So in fact, in the Aioli paper, we showed that a lot of existing methods assume the same dynamic mixing law, but the key difference was rather than fitting the parameters from exploration, they hard-coded them as functions of losses and gradients, as shown in the table here. So you can see that the A parameter of the dynamic mixing law varied significantly across methods. So for instance, Do-Re-Mi, one of the first data mixing methods, can be described as using a diagonal A matrix, while another approach called Doge constructs A based on gradient dot products. And the really neat thing is that the performance of all these methods is closely tied with how accurate their implicit mixing law is. So we found that when these hard-coded parameters were really far off from the fitted parameters, this also correlated with cases where the corresponding method performed poorly. So you can see in the figure here, the x-axis is the similarity between hard-coded and true mixing parameters, and the y is performance improvement. And you can kind of see that there's 2 regimes where the hard-coded values are quite off from the mixing parameters and performance is bad, and cases where the hard-coded parameters are quite close to the true mixing parameters and performance is good. So in short, the mixing law provided us with a tool to really understand the consistency and the robustness of a wide variety of existing methods. Finally, I'd like to talk about how mixing laws can help us understand how models learn from data. And I think this is the really cool part that has so much potential and future directions. So recall that this is the mixing law form we have discussed, and we can interpret this as each domain contributes this AIJ score for how much domain J impacts validation dataset I. So the big question one may wonder is, what does this A matrix across domains and validation datasets look like? And we would like to know this because you can imagine that there's a sort of like trivial A that is really sparse. For instance, every domain only influences the performance of itself, and if A didn't change at all over time. So there's this sort of like, maybe the true A matrix is a very simple structure, and life is easy and data is independent. But we actually find quite the opposite. So first, we find that this A matrix has quite some asymmetries. So it's rarely the case that one domain only influences one task. And instead, we can have many similar domains interacting with each other and similar validation data sets as well. So on the left here is a figure from the data mixing laws paper that shows that there are off-diagonal interactions among different domains. On the right here is an unreleased figure from some work of mine that should be coming out soon, where we looked at a set of domains that corresponds to topics on the web, and our validation data sets are downstream tasks. So I'd like to kind of look at a few examples of rows in this matrix. So in this figure, we can see that there are some tasks that are only influenced by one domain mainly. So for instance, MedMCQA, which is a medical health task, is most influenced by health data, which makes sense. But it's pretty cool that this is being backed out of this, this sort of mixing law experiment. However, there are other validation tasks that are influenced by multiple domains. For instance, this humanities task, MMLU Humanities, is influenced by crime and law, history and geography, politics and religion, which makes sense intuitively. Similarly, we can see that there are some domains that only impact one validation task. For instance, crime and law really only impacts the humanities task. But on the other hand, we also see that there are some domains that can impact multiple tasks. For instance, there's this science, math, and technology domain, and it affects tasks ranging from ARC Challenge to Jeopardy, algebra, and so on. Finally, as a fun tidbit, these A matrices really can offer some interpretability as well and confirm that models are behaving as expected. So as an example, I've boxed two entries of the matrix here where we can see that food and dining and home and hobbies really influences this task called PICA. So I was really curious, and so I started digging more into how PICA was collected and what it is. So PICA includes questions around physical common sense reasoning, for instance, how to apply eyeshadow without a brush or how to bake a cake. And it turns out that PICA was constructed by scraping from this website called instructables.com, which in fact contains a lot of cooking recipes and home improvement articles. So now it makes sense that PICA is very influenced by food and dining and home and hobbies. So this is really cool because by looking at this learned A matrix, you can better understand what's in your data. So for instance, if I saw that science, math, and technology was not actually influencing all these science and math tasks, I would get suspicious, and I could use this A matrix as a tool to check if my data was collected correctly. Second, we find that the A matrix can change over time. That means that the relative influences of domains can evolve. So in the Aoli paper, we looked at training and evaluating on GitHub and C4 domains, where C4 is a clean version of the common crawl web domain. And we saw that the A matrix changed dramatically from step 2000 to step 4000. So in particular, at step 2000, you can see that GitHub's influence on GitHub is 0.63, and C4's influence on C4 is 0.37. So there's quite an asymmetry in what data sets are useful in this earlier stage of training. But once we go to step 4000, things start equalizing a bit. So both GitHub and C4 have influences around 0.48 on themselves. And so this kind of shows that as the model is trained, the relative importance of data is also changing. So to wrap things up, today we talked about the data development pipeline, which can be broken down into some rough stages like data acquisition, data transformation, and mixing, which improve quantity, quality, and composition. We then went into detail about how mixing is an inevitable step in data development and is used to create training data sets that aim to optimize a wide variety of model capabilities. And in the mixing literature, a key development that I'm very excited about is the fact that at pre-training, performance has this really nice, roughly linear structure in the data mix. And this suggests that mixing methods should be designed to exploit this structure to produce better mixes more efficiently. Finally, there's a few directions that I've been quite excited by. So first, a domain can really be any group of data. Typically, people think of domains as data sources, so think of things like comment, crawl, GitHub, and archive. But recent work show that domains can be defined in much finer grained ways, capturing other aspects of variation. For instance, one paper explored splitting web documents, not just by their source, but also by their topic versus their format. And I think the fact that mixing this general procedure is kind of agnostic across whatever your data is quite powerful, which is why I think a lot of the ideas here can hopefully be used in robotics. And second, an understudied aspect of mixing and really of all these data curation strategies is the feedback loop. So from these heat maps I showed earlier, can we use our understanding of how models learn from data to actually design and collect new data? In practice, people who are training these models already obviously do a heuristic version of this. You try some data, you get a sense of, how the model is doing, and then you go out and gather some more of your good data. But turning this intuition into a more principled process could be very powerful. And that's it. So I've listed some suggested resources on general data development and mixing for LLMs. And yeah, I'll take any questions.
In the interest of time, we're going to move on to the panel discussion.
Your panelists now be great for the cover. So those sets of your
Divide out by still on taste. One more chair.
Yeah, we did this with the chairs.
Okay.
There's some microphones.
Yeah. That's fine. All right, so for the last part of this workshop, to conclude today, we're going to have a panel where we're going to see all the hot takes on whether data is more important, the model is more important, and what part of the data is most important in training models. I'm going to introduce our moderators here, who are fantastic organizers, Chris and Joey. Joey is a PhD student with Dorsa Sadik at Stanford University. Chris is a PhD student with Jeanette Boat at Stanford University, and they have been some of the drivers between all of the events that you've seen today. So you should thank them for all their efforts today. And then we have all of our panelists here today giving talks, and you've seen them before, but I'll quickly reintroduce them briefly. So from for you left to right, we have Max Simchowitz, who's a professor at CMU. Then we have Ashwin Balakrishnan, who is now a research scientist at Physical Intelligence. We have Mayee Chen, who is a PhD student at Stanford University and affiliated with AI2. We have Chelsea Finn, who is a professor at Stanford University and one of the co-founders of Physical Intelligence. We have Masha Itkina, who is a research scientist at Toyota Research Institute. Ken Goldberg, who's faculty at UC Berkeley and co-founder of both Ambi and Jacobi Robotics. So with that said, I'll kick it to our moderators and hope you enjoy the panel.
All right, thanks, Rohan. In the interest of time, let's go ahead and get started. So just to kick it off, the first question, very basic one is, and also a difficult one might be, how should we define good data? So how would you think about what makes data good or bad? And maybe I'll kick this one off to Ashwin, who we haven't heard from yet.
Sure. Yeah, it's obviously a tricky question. At the end of the day, when you decide what data to collect or what data to curate, what data to keep, it's a decision about like what capabilities you want your model to have. So your data should reflect the kind of behaviors you want your model to produce. And I think at the end of the day, one of the most consistent properties of good data that I've noticed is that, first of all, your data should reflect, those capabilities that you care about. And second, it should be the case that like, no matter how messy or chaotic your data collection process is, it should be the case that, given an input, no matter how you design your algorithm, it should be that like, the entropy of the output is like relatively low. Like it should be relatively clear how to generate the outputs in your data set, given your input. This doesn't mean that you necessarily have to collect like super narrow data sets. It should just be that you have designed your data sets and your learning algorithms together so that you can actually break out the multimodality of the problem effectively, so that you can prompt for the behaviors you actually care about the problem.
Yeah, go ahead. Oh, the mic should all be on.
No.
Yes, okay, great. I think the answer to that for me is whatever data makes your success rate go up. Now, the success rate is on is another question, right? It might be a super narrow, very specific problem with all the same initial conditions, or it might be 17 different tasks and you're looking at average success rate overall. As long as success rate is going up on whatever problem you set up that you care about, your data is good.
Yeah, I'm going to push back on that a little bit. Masha, I mean, I think it's the success rate as metric is a little bit of help out. We were talking today about speed of performance, for example, right? So there's that factor, there's the consistency of robustness, right? Because I think there's also, when you say success rate, there's a lot of questions about what is the distribution, right? And if it's robust, so variations in the distribution is in a way success rate is measured that, but it really depends on how much you're testing in that distribution. And so I agree with you in general, but I want to also talk a little bit about Ashwin, because when you say low entropy output, are you suggesting instead of being unimodal?
No, so I guess it depends. It should be like unimodal, like based on what you're conditioning on, right? But for example, maybe you have a data set where like there's like many ways to do a test. I think that's okay as long as like you have information about like what those different ways are. So if you like have some sort of labels like, oh, like, this is like one strategy I follow to do this task, there's another strategy I follow to do this task.
Yeah.
If you have that information that you can actually condition on, then having like a multimodal data set is fine. Okay. But I think you should have low multimodality but conditioned on all the inputs.
Okay. Because I was also going to say, one other question related to this is that good data, but can that data be clean effectively, right? Because we have data that's easily cleaned. It might be not great data to begin with, but it has nice quality, so you can clean it. And so I'm sort of getting that, which is there are going to be these ways to fix that entry after you.
Maybe just one thought to respond. Thank you for calling me up. Success rate. I wasn't criticizing. Success rate is one possible metric that we care about. Yes, let's generalize to any metric that we care about. But you can also think about robustness as whatever task set that you design, right? So maybe you care about many different failure modes, and you design your ICs to be adversarial. And then you're thinking about either success rate or whatever metrics you care about in the context of this very robust thing.
One thing that I'll mention a little bit is I think that, I mean, generally, I completely agree that you always want the data that's going to make the model better. I think that unfortunately, like I actually mentioned in my talk, I think that measuring things like success rate for generalist models is increasingly hard, really, really hard. And so I think at the end of the day, it's like the most practical thing is going to be you have to make choices without being able to measure if those choices are impacting the right choices. when we're collecting data at scale, specifically, especially when data is going into training these generalist models. There's a lot of really nuanced things. I mean, there's things like being able to complete the tasks like quickly, being able to have like high success rate, diversity, like lots of environments, lots of tasks, and so forth. But there's also really nuanced things like, will this data lead to liquid following? And if, for example, you're in a scene and the robot always does the same thing in that particular scene, then you can then condition the model in language, it might completely ignore language. And so, yeah, I think there's a lot of nuances to it. And that's also something that, like, if you tell someone who's like operating the robot is to researcher and tell them like they want that, maybe you don't want partial observability, they don't know what you're talking about. So it's actually really, really hard, and lots of attention goes into getting the data.
Yeah, so to build up on what you were just talking about, to what degree do you feel just nuanced aspects of data quality or characteristics of the data that leads to desired behaviors can you preempt versus sort of just recognize at deployment time the model function have to work backwards from there? Are there some practices that
yeah, I think it's going to be a mix at the end of the day. I also think that maybe you like collect it is like train on and you see what happens. You then try to correct that. No, you don't just start for it on that task, you start for it on all the tasks and kind of put together a process of it. So each the kind of data that you want. Yeah, and so for example, like for partial observability, you notice that like, oh, you really need to have like Goldberg in the image at the start of the episode to get the robot to work. It's like really not working. If you don't do that, then you kind of set the data goes to do that.
What we found to be most effective, it's really hard to guess what exactly is going to be the right data before you start. So we have this iterative process where you'll collect some, you'll train a model, you'll watch some rollouts, you get a sense of how it's performing. That's how researchers also do it, right? But it also really works for the robot teachers. So as long as we're able to close the loop and show them what the data that they collected resulted in when you roll out the policy, that really helps them adjust. It doesn't always work, and it can take multiple tries, and maybe you go the wrong way to try to do recovery, and you have to go back, right? That's happened, but I think closing the loop has been very effective.
you're saying with the contractors?
With robot teachers.
With robot teachers. Interesting. Because I was actually curious about that. You have more personal experience than me. I was just curious about how sophisticated are they in the sense that do they, first of all, I'm curious, there's a lot of turnover and people burn out, and those that don't, are they really getting into it and really learning how to define nuances? Because I just don't know.
Yeah, in our case, there hasn't been too much turnover, and we're not at the same scale as Pi, so I'll let Chelsea speak to that more. But for us, it's very clear that the longer they are with us, the more proficient they become, and the more they know sort of the nuances. Oh, we have to collect in this way for this kind of task because that would result in a just because they get it from experience and iteration.
Yeah, on the turnover part, we've been kind of quite happy with what we've been able to do there and sort of at least time. One thing I actually want to mention on like some of your previous point is that for the with regard to like measuring how good your data is, when we were working on the Detroit data set, at the beginning, and then maybe for the Detroit data set, like 8,000 trajectories, ballpark, and 500 scenes, 50 environments, really diverse camera viewpoints. When we were first trying to train on it, like a lot of policies were not working really on the data set, and we weren't sure like maybe this data set is not dense enough to be able to train good policies on it, or maybe like we thought that maybe there was something fundamentally wrong about the data set. It wasn't until I think maybe a year later, when CoRL trained like the Kaiser fast model, that we actually saw a model with like a policy trained on it that zero shot did something out of the box and worked. When it did, it actually worked really well in a generalist studio environment. So it kind of sometimes said like it goes to show that like if your data is like a little bit too far ahead of your model development, then you might have this really painful time period where like you just waste a ton of like time and resources on collecting this data set. And maybe it like just didn't turn out. And so having a bit of a feedback between the data and the policy training is really helpful. At the same time, I'm really glad that we deployed it, even though that feedback loop wasn't as tight as it could be. It pushed us to like build better models that can use that diverse data.
So we've talked a lot about what makes good data so far. And one interesting thing is currently there's a lot of companies that are trying to collect robot data and sell it to other people. So a short question to everyone would be, do you think this would work? And if not, why?
Yeah, I think generally in the long term this should work. I feel like if we're not able to, consume data from like very diverse chaotic sources, then there's some problem with how we're doing algorithm development. But I do think like since the data is like so important to developing like generalist models, like having kind of like this Chelsea said, like a super tight loop between like data collection and policy learning is like very critical, I think, in these like early stages of robot foundational development. I'll say like from I guess like my personal experience, especially when you're collecting data sets for like these robot foundation models, like it's hard to even keep track of like what are the tasks in your data set. Like it's just ballooning. There's like not like really like a clear like delineation between like this one task and another. So often the way I find out what's in our data set is just by playing with them off. Which like maybe ideally in the future we have like a more coherent way to do that. But often, when we're trying to help find with the capabilities you want, it's like very useful to like be able to immediately say like, okay, I'm going to collect data in exactly this way, so I can patch this to I know this and playing with it. But I think once we hit a point where we have like mature data collection strategies, which we know will lead to specific capabilities internally, then like we'll probably move to a regime where like we can more effectively ingest data from other people with strategies and so.
This may be vaguely tangential, but if we kind of chart the development of large language models, what we really see is that currently like most kind of valuable data is human data that labels preferences for positives and negatives. And so we've heard like a lot of really interesting comments on how to collect good positive data. But I think as soon as we develop the methodologies and models to incorporate negative data, probably like the span and kind of methodologies for collecting negative data will be not only expanded, but probably your end users will then be able to provide negative data. Like being able to get failure examples from your users probably would, like if you're envisioning what does like the robot data company look like, I would imagine some software as a service for like, like you can sell like a solar power back to like your, electric company. Maybe you can sell bad data or negative examples back to your robot company, provided you have a good Q learning algorithm to handle that.
Yeah, I agree with that. I think that we're going to care a lot more about negative data and good negative data in the future. One kind of recent anecdote is, we've been working on a benchmark for reward models, like general purpose reward models for robots. Hopefully we'll release it soon. And one of the things that we're working on is when people want a data set, this reward model benchmark, and then we're like, oh crap, like the data set all has successes. How do we benchmark rewards if we don't have failures? We haven't done all the safety research. What we did is we took hindsight, for people who know hindsight experience replay, we actually did the opposite. So we turned successes into failures rather than turning failures into successes to generate labels to augment the data. And yeah, I completely agree that more negative results.
I also explore more role modeling and things like that, right? I think ultimately you have some way to post label or curate your data. All data would be useful in some way. Yeah. No, I was just gonna say that having a talk today was about failure detection, right? So thinking about all the different applications that if we can detect these failures, then we can do recovery, we can think about curation, we can think about how we mitigate these data failures, right? All these different things and world models, right, will unlock so many different capabilities. I think it's great that these companies are collecting all this data, even though it's not all high quality, as long as they're doing it ethically as well.
Okay, so let me also try to be a little contentious and suggest, do we all agree that it should be diverse? And what I'm thinking of in particular, this week we've seen these great demos of laundry folding, towel folding, right? Out of Dyna, where they're just folding one towel over and over again. And then Generalist just released a demo of this Lego assembly. And in I don't know which way this general model. They sort of put in this, but it seems like it's been very fine-tuned on this Lego task. It was an impressive task, very impressive. So I'm just wondering how do the other panelists feel about diversity versus, sort of top down, starting very generalist, and then training generalist models versus this approach that some are taking, which was bottom up, training very specialized models first. Now everybody hates me.
Well, so I think that companies like Dyna and Reynolds are using kind of a very general purpose pre-training models and then figuring out how to adapt them. I think both the diverse pre-training and specialized fine tuning are really important and valuable problems. And the specialized fine tuning is the thing that will, at least in the short term, probably be quite important for actually getting these robots in the real world. So I think it's like figuring out both parts of that puzzle seem really important to me. And the diversity of data is like, I think they're really critical for that first part. And I think we omit, I guess one thing that we found in Pfizer is if you omit the pre-training, like a lot of your company doesn't work. Because you need the pre-training to help it understand what to do in like various cases. Like if the shirt is like configured in a weird way that you didn't see in the post-training is that pre-training helps back it up. And that's one of the reasons why I think like diverse strategies and pre-training is good, is to get more exposure to diverse states. So yeah, I think both are.
Well, so you've talked a lot about various aspects of data that you might want to target in the collection phase. Talked about how different types of learning objectives, between prediction learning and role modeling, they benefit from different kinds of data. But we're talking a lot about us as building human teams, to collect data for us. In 5 years down the line, or let's say by 2030, are we still gonna be collecting our own data, or should the strategy be to accelerate as fast as possible to the point that we can be deploying models and having robots collect data for us, kick off data flywheels and things like this?
Well, I think unlike in say like applications like AEs, for example, where it's like a super safety critical application. I think robotics actually we can get to like calling about flywheels without like having like near perfect performance for some tasks. Right? So I do think like right now maybe a lot of like the generalist robotic work is like kind of at this point of like, what is the strategy we can take so that we can get over that hill, so that like people will want to start putting this into a flywheel. And then once we get there, we can improve pretty quickly. And I do believe that like, doing large scale robot data collect is like one of the best ways to kind of get over that bump initially. And then once you have like, flywheels going for a bunch of diverse tasks, then I think you can like really get into the floating amount of data you get, and as a result, the capabilities.
Robots to do more work.
Oh, sorry. Maybe a small thing to add as well. So when services for some of these robots become products, we're going to start demanding success rates that are far above probably some of the things that we're seeing in our current models. And it will end up being actually unavoidable for the robots. We'll have to collect data on those tasks, because otherwise we won't be able to see the tails of the failure distribution without having some of that. And I imagine also algorithmic things will change as well. Like hopefully once pre-training is good enough, we can actually get reinforcement learning to work in a very reasonable way. We can still explore from very good priors. We'll be able to use VLAs for good task decomposition. And so I sort of imagine that it's not even going to become something that's sort of more effective. It's going to become something that's a necessity.
I think there's probably two parallel threads there. One is construct a deployment site where we know that we're safe and there's probably no things around it in close proximity, or they're safe from whatever the robot can do. And I think that's a good idea. I think that would drive progress, and we should do it. But simultaneously, we really need to be thinking about how to get to the point where we would feel comfortable getting these workplace systems in environments where there's I think that's the ultimate thing that a lot of us would like. And there we still need to do a lot of research similar to the trajectory of, this is like way on the autonomous driving. Where we really have to make sure that we remain safety critical and we really figure out those safety pieces.
So I'm not saying, I'm curious how others feel about this in terms of my sense is we should do whatever is needed to get to that. Where you get the flywheel going, which is often a mix of the old fashioned engineering with the models. And I'm just curious how others feel about that. Are you opposed to this in principle? No. You're not opposed? You are. I'm not opposed. Okay. Justin. Afterwards opposed. I'm just curious. I'm just curious if you see that point because sometimes it's not either or. You get up to speed, and then once you collect the data, then you can gradually, pare back those other modules so it becomes end-to-end efficient.
No, and also, I think the perspective of doing what it's needed to get to the flywheel kind of like helps keep us honest about when our like aesthetic preferences are taking over. Right? So my personal background is actually from the theory of reinforcement learning, where we like sort of imagine, the baby in the world, it's drawn and it doesn't know what to do, and that's a big problem. And I think you have to come to terms with sort of like what are actual problems, and I think that by good engineering, you sort of put yourself in a regime where you're actually tackling what's relevant, rather than just kind of creating like academic fictions for the purpose of introspection. I mean, so it still can be valuable, but yeah, you should put yourself in a regime where you look.
On that note, I think that it would be interesting to toss the conversation over to Mayee. So Mayee just gave a great tutorial on data mixing for LLMs. And so one question I would have for Mayee is like, what should we take from LLMs into robotics? And for the robotics people, what should we ignore from LLMs?
Really good question. So I think in terms of things we can take, so pre-training data sets for language models are absolutely massive. And so a lot of times, again, people just try data selection technique on like one subset of the data, and they're like, oh, this worked, we'll just keep on using that thing. But there's actually so much noise in pre-training data that you really want to account for the effects of just like randomness and think about like robustness across even just like, you pick a thousand, a billion random tokens with this seed and another seed and seeing if these like data selection methods or data mixing methods are actually consistent across noise because there's just so much variation if you're looking at a web data set. So I think that's one thing that's really struck me in the language model space. I think things to ignore. I don't know if it's really something to ignore, but I think there's like something about the construction of language that's very broad and there's a lot of facts. So a lot of things can kind of be just memorized, where it's like you just train on the fact and then the model will know the fact. And I think that allows for a lot of data selection and data curation principles to be almost like cosmetic in a way. So the example I have is like all of these rewriting methods are like you rewrite this sample to the side with Wikipedia and it gets better. And so I think a lot of these language model data curation techniques kind of rely on our human intuition of what looks like your data. Be like, oh, this looks cleaner, this has the structure. And I think that's because language is just so broad that it's easy to kind of do this matching. But I think maybe for robotics, there's kind of this I think you care about how the robot does the thing and not just like success sometimes. And so thinking about like, do you want to create data based on these more like human intuitive, like this looks like good data or not? That makes sense.
That's a good question. Do you think there's a big difference against maybe like robot data currently is higher quality in common crawl, like where the people collect it and common crawl is like anything anyone says? So do you think that's changes how we think about things?
Yeah, I think definitely that changes things. Like the fact that
language data is so noisy, requires you to really like focus on consistency and robustness of these methods. So like if you try this method on like two different settings or like slightly adjust the objective and it's like working well in both of these settings, you kind of know that it's would on that noise. But I think if your data set is cleaner, maybe you have to worry about these things less. But I'm just thinking like as you scale up and get more data, maybe some of these issues will arise. Because you can't start keeping track of all the quality of everything.
With regard to the memorization and like all the factual knowledge, it's like inside these LLMs, it kind of makes me wonder if like robot foundation models will need to be quite as smart as a result because they don't need to memorize, like presumably they don't need to memorize so much like actual knowledge. Because usually you don't need to know, I don't know, like Shakespeare's birthday or something to like pull the title. Yeah.
Is there anything else we should ignore from language models besides the model size? Continuous actions versus discrete, a big problem. No, we should take all of the lessons from language models and just do it again.
One thing is that a lot of the controller takes to that you can like verify everything immediately, and that's like not true in any real world domains, but a lot of language model domains, and so that's gonna be a hurdle that like where we can't just like copy exactly what the domain. Yeah, but I do also think that there's a lot
I think maybe two very positive things. One is the safety information notice, especially as we know tomorrow with robots and that consequences to provide us the environment around it very, very quickly, which it could also have consequences and it's becoming more of an important thing and very more delayed. And the second one is I personally think that we'll be able to get to the scale of data that language has in the world, based on the demand and how much there is. So we're gonna have to be a little more creative in some ways with how we use the limited data that's available to us, whether that's for curation or mostly priors or obviously.
You know, one thing is Chen thought ideas and things like that. People are adopting that for robotics. But you asked a little bit of variation on that, which is what about how can you for this field that robot data can help, not maybe not LLMs, but DLMs improve? We've been doing some experiments with extracting data from actually Droid. We used a lot of that to generate PQAs and sort of a benchmarks, but also sort of training of those goods. There seems to be a feedback loop that you train the VLM on this robot data, then the VLM gets better at evaluating and cleaning with robot data. So I'm just curious how you feel about that sort of hybrid.
I'm hopeful. I think that we need the data to be diverse, and I think it's very important diverse data that can make better jobs. I think long term, hopefully improves the elements too. I think there's a lot about either just vanilla results that don't like really fully understand the world we live in because it's all through this mirror of human text, or through this perspective of human text. So yeah, a lot of embodied data. It needs to be diverse enough, it needs to be large enough, because that's where also we can have them be collecting the data, getting the experience in the real world. And so like, but it's not diverse enough, I don't think it will quite collect it.
I guess going back to Joey's initial question, I think one other maybe obvious thing that's like pretty different between like LLMs and robotics is that like for LLMs, like the pre-trained data set already largely exists, right? The internet, while robotics is collecting that for the first time. I think that comes with both challenges and opportunities, right? Obviously, ideally we would have this whole robot data set already. But now that we get to make all the decisions on how to collect it, I think like there's a lot of interesting questions on like what is the right composition of a pre-training data set so that you can like quickly fine-tune later or list the behaviors you want. Like I think maybe on the LLM side, we have to think about the questions in the exact same way because we have a lot of the data already and maybe we'll do a lot of data like later more for like post-training and getting like really good performance.
probably have time for one more question here. So, we're talking a lot about the relative size of the training data sets, models, robotics. There seems to be some convergence on the idea of like data flywheel being important, but that being contingent on a certain base capabilities of the model. Masha, you said that collecting the human files is probably the best way we know how to do that right now. So, on that premise, you could dedicate all robotics researchers to, let's say, a year's worth of data collection to create that pre-training data, rather than all the research they would produce. Would you give it a second? Interesting. I mean, I don't know. Actually, I don't know if robotics researchers are like the best and necessarily going to data. Might not be. Yeah. But yeah, I mean, I think it'd be great if we have like a large number of people who are like collecting data. I think like long term too. I mean, maybe this is kind of like a pie in the sky notion, but like it would be nice if there were like economic incentives as well for like people to end up like collecting robot data anyway. So, these aren't concrete ideas, but like, maybe if there was like, a game that everyone really like playing, where like, the process of playing that game, you end up collecting a lot of data, or something that would like get people incentivized and excited about collecting robot data that we can just use as a research community. That feels like something that would be a really cool way to spend time.
Yeah, I completely agree. I was gonna say, gamify the data collection, but to answer your question, no, I think the robotics community is too small and it will actually make a difference.
So I would say that was like sort of, in some ways, some of our initial ideas were great. It's like, it's 30 years of data collection, and we were originally scheduled within the lab. But then we asked the people like what they wanted for data, and they wanted to be community, and everyone said yes. I'm like, okay. The people liked it, and we just thought, what I think is great about our community. I think that now that we have ways to have other resources for stocking data, and we know. But I think that if we didn't have those kinds of resources for stocking data, then I definitely yes. I do think that like despite maybe limited collaboration capabilities, I think that researchers have a lot of intuition for like how to set up the scene in a way that leads to data that's really good for the model. So researchers I think would actually much with excellent data.
Speaking of gamification, I mean, in some ways, Chelsea, I remember when you said the objective, if you put in 40 hours of data, it would be a cloth of paper. Right? That worked for a lot of my students. It was really effective. And it was kind of gamification, and it worked. It was really clever. I think that is interesting. I'm not sure I like it. And especially if it's a fun game like Pokemon or something, that's great. You could really go out and get a huge number of people. I was also thinking something like a Peace Corps. So, because I do think it's actually helpful for all of us to do it, mostly because we can learn a lot from what it's like. I mean, it can be incredibly tedious, and I think to know how that is, and then think about how to help the contractors and guide them and supervise with them and then maybe design that next generation of interfaces that makes it more palatable.
To that point, a lot of the past papers that I've published in the last year or two have been inspired by sitting there and watching other Black teachers work and seeing their pain points and what works and what doesn't. Right? Data curation is a way to help them get to a place where the policy better, even though they don't need to figure out the exact mighty things that they need to stop doing or not turning on. So it is very powerful, and I do recommend that people watch data collection or do it themselves.
I have 2 hot takes. You guys want a hot take?
Yeah.
So I think all these we start thinking about specifically like I think this is being really helpful for me coming from outside the field is like seeing like the weird minutia and details and idiosyncrasies of things that you can only really get by being around Harvard, being around the data collection. But maybe my 2 hot takes are first, even if it's the thing that can move robot learning as a field the most forward, we still also need to preserve kind of like certain cultural norms of academia so that like students also have practice like going around and wandering in the wilderness and like not really knowing what they're going to figure out, or like asking questions where they get a little bit lost, because inevitably you'll run into challenges that our current paradigm doesn't hit. And if students aren't both given like experience with what is working and sort of direction, but also like experience trying things out that are somewhat kind of off the beaten path, I think we'll find stumbling blocks later. And I think the second hot take is if we have a lot of people, we gamify making data, then there needs to be like some sort of social dividend that like repays that to people. Because inevitably that data that we'll collect, a few people or actors will be able to take advantage of it and like do really, really well. And you know, we're not set up as a society or as an economy, or at least in the US, we're not, I don't know how, hopefully things are better here, but we're not set up in the United States to kind of allow people to like really reap the benefit of the economic sort of utility that they're generating by collecting these data. And I don't really know how we solve that problem.
Anyone else? No one wants to vote for the data. All right. With that, I think we have time maybe for one audience question, and then we'll wrap up the panel. Does anyone have a question? No. That's also okay. I guess we can end with another very, very quick question, which would be, in 5 years from now, do you guys still think that we will be trying to collect large data sets for imitation learning? Or do you think we will just be doing something entirely differently? And why might that happen? Will it be because imitation learning will work in 5 years? Or will it be that like there's some other breakthrough that leads to a totally different direction for the field? Maybe that's too hard of a rapid fire. That's an answer to the question. It's good.
RL plus like targeted task specific data collection, like to warm start the RL.
All right, I guess we have one or two predictions.
I'll say, I think that we're waiting for a breakthrough in simulation, which could pop in at some moment and that would change things dramatically. Or let's say video analysis, right? 3D video analysis, there's breakthrough that could happen there. So people are working on both those fronts, and if those happen, that would change.
This is maybe the opposite of what I say, but I do think it is really valuable for different parts of the community to work on different problems, and not everyone to be kind of going to a single approach and that sort of thing. So I guess that there will also be kind of a diversity of approaches in 5 years. And there's one that I'm betting on, but I also think that other people will be betting on all sorts of other things.
Can I ask about that? I mean, I go back to your quote, which I loved earlier, don't be a purist. And it does feel like a lot of the talks where it's imitation learning or it's reinforcement on the chain of thought is even so. Do you guys see hybridization of this, or is it everybody's got their own language?
RL only works with pre-training.
RL is with the imitation and then RL imitation is. But at least that's my take. And other ways of hybridize that people like using simulation with this, or using control theory, or using neural models, or all sorts of things.
All right, I think it's time to wrap up the panel, but if you guys have other questions about other things, like maybe feel free to find them at some point, but I'm sure they also all have many things they need to go do. So let's go thank the panelists, and then we'll get on to the world. Thanks so much. Thank you, sir. Thanks so much. Thanks, man.
Where did you saw it? Yeah.
I sent it to you Slack. Here. Just.
Dude, nobody cares.
Yeah, no one cares.
Oh my gosh, it's fine.
All right, thanks so much for presenting one more announcement at the very end. We do have one best paper award today. So, yeah, with that ahead, we had
4 nominations. Okay. Yeah, so the 4 spotlight talks were all nominated for the best paper award. After some long and difficult deliberation, we have given DataMill the best paper award. So if you're from DataMill, please come find us later. We'll email you a certificate and some other information. But yes, thank you all for attending. Cool. That's it. Cool.
That was fun.
That's good. That's good. That's good. I tried to be spicy.